Hi everyone, welcome to goclasses. In this lecture, we will continue our discussion of average memory access time in context of cache memory. So this is average memory access time AMAT part 2. So if you did not watch the part 1, you can watch the part 1. The link of average memory access time lecture part 1 you can find in the description, also in the pinned comment. You can check it out. So in the previous lecture, we have studied these concepts. We have seen the concept of memory hierarchy, hit rate, miss rate, hit time, miss penalty. All these definitions we have seen. Average memory access time for single level cache. So these concepts we have already seen in the previous lecture. In this lecture, let's start with discussion of multi-level caches. So we want to find the average memory access time for multi-level caches. We have already seen that in our computer systems, in modern computer systems, we don't have single level cache. We have multi levels of cache memory. And the cache memory which is closer to CPU, which is closest to CPU, that is called primary cache, or I can say level 1 L1 cache. Then you can see, if you have, let's assume, three levels of cache memory, then that will be called L1 cache, L2 cache, L3 cache. Okay. And I told you that the size of these cache memories, that will increase from L1 to L3, and the speed will decrease from L1 to L3. Okay, very simple. So let's discuss what will be the average memory access time formula when we have multi-level caches. Remember, the concept is same. For every memory access, whatever memory request CPU generates, for every memory request, we will always check the L1 cache first. So when the CPU will generate the memory request, then we will go to the L1 cache. We will find whether there is a hit or a miss. If there is a hit, then immediately the data we will send to CPU. But if there is a miss, then after that we have to pay the penalty. What is the penalty? If there is a L1 miss, then we have to access L2 cache. If there is a hit in the L2 cache, then we will transfer block of data from L2 to L1, and then from L1 we will transfer a word to CPU. Okay, so you can see, if there is a L1 miss, then we will access the L2 cache. Remember, for every L1 miss, we will definitely access the L2 cache. Yes or no? Similarly, remember, for every memory request that CPU generates, for every memory request, whether that is available in the L1 cache or not, whether the data is available in the L1 cache or not, for every memory request generated by the CPU, always this L1 cache will be accessed. First, we will access the L1 cache. We will find whether there is a hit or a miss. So L1 cache we always have to access. Now, in the case of miss, I can say, when there is L1 miss, then always we will access L2 cache. If there is a hit in the L2 cache, then we have seen that block will be transferred from L2 to L1, and word will be transferred from L1 to CPU. But remember, if there is a miss in the L2 cache also, then we will access the L3 cache. So for every L2 miss, we will definitely access the L3 cache. So when there is a L2 miss, then we will check in the L3 cache if the data is available or not, if there is a hit or not. If we have L3 hit, then we will transfer the block of data from L3 to L2. From L2 to L1, we will transfer a block of data. And from L1 to CPU, we will transfer word. Okay. So remember, for every L2 miss, we will definitely access the L3 cache to check whether there is a hit or a miss. If there is a L3 miss, then we will go to main memory. Then we will access main memory. So when there is a L3 miss, then we have to access main memory. So from main memory, we will transfer a block of data to L3. From L3, a block of data to L2. From L2, a block of data to L1. From L1, a word to CPU. Okay. So this is the concept of memory hierarchy. We have already seen in the previous lecture this concept. We have already done the revision. Now let's find the average memory access time formula from this concept that we have seen. What is average memory access time? This is the access time on average seen by the CPU. Okay? Because remember, Sometimes the CPU will get the data in L1 cache. So sometimes the CPU will see very less time. Sometimes the CPU will get the data in more time because there can be L1 miss. If there is a L1 miss, then it will take more time to access the data. So from the CPU point of view, CPU does not know about the levels of caches. CPU does not know about the cache memory also. CPU only knows about the main memory. CPU will generate the main memory address. With that address, first we will go to the L1 cache, then L2 cache, and so on. But remember, CPU is thinking that there is only main memory. Now, sometimes for some memory request, CPU is getting data very fast because there is a hit in the L1 cache. But for some data, there is a miss in the L1 cache, there is hit in the L2 cache. So for some data, it will take more time. And there is some data which will take a lot of time because maybe there is a miss in all the levels of caches. So we have to access the main memory. Okay, so that is the reason I can say what CPU is thinking. CPU is thinking that for some data I'm having very less delay. I'm getting the data very fast. For some data, I'm getting the data in more time. Okay, and for some data, I'm getting the data in very long time. So we want to find the average. What is the average memory access time seen by the CPU? That is called average memory access time. Very simple concept. So we need to find the average memory access time formula. I told you that to find the average memory access time, we need to consider the hit rate of L1, hit rate of L2, hit rate of L3. The hit rate of main memory is always 1 because this is the last level of memory hierarchy. So this will always hit. I can say the hit rate of main memory that is always 1. For the last level of memory hierarchy, the hit rate is always 1. Okay, so we need to consider the hit rate of all the levels of caches. We also need to consider the miss penalty. We also need to consider the frequency of different type of accesses. If there is a read access, write access, okay, read request, write request. So the frequency of read request, frequency of write request, all these things we need to consider if we want to find the average memory access time formula. So let's find when we have multi-level cases, then what will be the average memory access time formula? Let's find. But before that, let's do the revision of hit time, miss penalty, all these concepts that we have already seen in the previous lecture. Let's do the revision of them. This hit time concept we have already seen in the previous lecture. I told you that cache memory hit time, that is basically same as cache memory access time. So this cache memory hit time and cache memory access time, these two terminology we use interchangeably. For example, L3 cache memory hit time, that will be equal to L3 cache memory access time. The definition of hit time you can see here. This definition is taken from Patterson and Hennessy book. So you can see the hit time definition, that is the time required to access a level of memory hierarchy. For example, if you focus on L3 cache memory, what is L3 cache hit time? So that will be the time required to access L3 cache, including the time to determine whether there is a hit or a miss. So for L3 cache, what will be the hit time? Focus on L3 cache. So the L3 cache hit time, that simply means the time required to access this L3 cache, including the time required to determine whether there is a hit or a miss in the L3 cache. Okay, very simple. So this is the definition of hit time we have already seen in the previous lecture. And remember, cache memory hit time is equal to cache memory access time. So L2 cache hit time will be equal to L2 cache access time. L3 cache hit time will be equal to L3 cache access time. Very simple. Okay. In the previous lecture, we have seen the definition of miss penalty. The name itself is telling you miss penalty. Penalty means extra cost that we have to pay. Yes or no? So remember, miss penalty means after the detection of a miss, after case miss is detected, after that, the whole extra time taken, that will be called miss penalty. So you can see miss penalty means penalty of a cache miss, cost of a cache miss. So remember, the miss penalty is basically the additional time required for an access when there is a miss. So in the definition of miss penalty, we do not include the time to check whether there is a cache hit or a cache miss. That is the reason you can see here miss penalty simply means after detection of cache miss, means we have already checked in the cache memory. If there is a hit or a miss, we have already checked it. We have already found that there is a miss. After that, after finding that there is a miss, then the whole time taken, you can see the whole time taken after that, that is called miss penalty. Very simple. For example, what will be L2 cache miss penalty? That means after the detection of L2 cache miss, we have already checked in the L2 cache whether there is a hit or a miss. That detection we have already done. Now, after the detection of L2 cache miss, the whole time taken after that, that is called L2 cache miss penalty. So L2 cache miss penalty simply means the additional time required when the data is not in the L2 cache, when there is a L2 cache miss. After L2 cache miss is detected, after that, the whole time taken after that is called L2 cache miss penalty. Very simple. So the name itself is telling you miss penalty means the penalty of a miss. After the detection of a miss, what is the penalty that you have to pay? What is the additional time that is required to access? That is called miss penalty. Very simple. From this diagram, let's try to understand what is L2 cache miss penalty. Very simple. When there is a L2 cache miss, then always we have to access the L3 cache. Always. Whether there is a hit in the L3 cache or whether there is a miss in the L3 cache, we will always access the L3 cache. So I can say that this L2 cache miss penalty, that simply means we will always access this L3 cache to check whether there is a hit or a miss in the L3 cache. If there is a hit, then that's it. We basically, if there is a hit in the L3 cache, then I can say that only this penalty we have to pay. The penalty, that simply means L3 cache access time. That is the penalty when there is a hit in the L3 cache. So I can say that penalty is simply L3 cache access time. But remember, if there is a L3 cache miss also, then we also have to access the main memory. So I can say that this L2 cache miss penalty, that will that will be a formula. I can say L2 cache miss penalty will be simply a formula. What will be the formula? When there is a miss in the L2 cache, then always we have to access the L3 cache. So I can say L3 cache access time plus the miss rate of L3 cache multiplied by the access time of main memory. I hope you understood. If you did not understand, don't worry. We are going to see the formula. But I hope you understood that once we have found that there is a L2 cache miss, there is a miss in the L2 cache. Now, after that, we always have to access the L3 cache. So I can say the L2 cache miss penalty, that will be equal to L3 cache access time plus when there is a miss in the L3 cache, means miss rate of L3 cache multiplied by main memory access time. Yes or no? Understood this? Let me know. Very simple. So let me tell you that this L2 cache miss penalty, that means we will always access this L3 cache, and this main memory we will access when there is L3 miss. Okay. And this we will always access when there is L2 miss. This we have already found that there is L2 miss. Okay. So I hope this diagram is clear to everyone. So let's see what will be the L2 cache miss penalty. L2 cache miss penalty, that will be equal to L3 cache access time, L3 access time, or I can say L3 hit time. This L3 cache access time, this you can also call it L3 hit time, L3 cache hit time. I told you that we interchangeably use these two terminology. So L3 cache access time, that is equal to L3 cache hit time plus the miss rate of L3 miss rate multiplied by when there is L3 miss, then we have to access the main memory. So when there is L3 miss, then multiplied by main memory access time. Okay, main memory access time. Please tell me, is this point clear to everyone? In the previous lecture, I told you that for the last level cache, the miss penalty is same as main memory access time. You can see for L3 cache, what will be the miss penalty? After the detection of L3 miss, we have to access the main memory. That's it. Yes or no? So you can see this L3 cache miss penalty, that is same as main memory access time. Agree with me? So you can see, because this L3 cache, this is the last level cache. This is the last level cache. Or I can say this is LLC, last level cache. So you can see for last level cache, the miss penalty is same as main memory access time. Okay, because when there is a L3 miss, then we have to access the main memory. If there is a L3 hit, then we never have to access the main memory. So what is L3 miss penalty? L3 miss penalty means after the detection of L3 miss, we have to access the main memory. So L3 cache miss penalty is equal to main memory access time. This we have already seen in the previous lecture that for the last level cache memory, always the miss penalty is same as main memory access time. You can see this screenshot is from IIT Delhi Professor Samriti Sarangi. So you can see that if L2 is the last level, let's assume if L2 is last level cache, then L2 miss penalty that will be same as main memory access time. You can see this screenshot is taken from Georgia Tech University. Here you can see that for the last level cache, the miss penalty is same as main memory latency or main memory access time. This is very simple because when there is a miss in the L3 cache, then we have to access main memory. Okay, so L3 cache miss penalty, the cost, the penalty that we have to pay when there is a miss in the L3 cache, that is main memory access time. We have to access the main memory. Very simple. Now let's come back to average memory access time formula for multi-level caches. So the concept we have already seen. Now that concept we need to convert into a formula. So let's see the average memory access time formula. Let's write. Let me tell you what is L1 miss penalty. What is L1 miss penalty? L1 miss penalty means after the detection of L1 miss, the entire time taken, that is called L1 miss penalty. Yes or no? The entire extra time taken, that is L1 miss penalty. Similarly, what is L2 miss penalty? That is after detection of L2 miss, the entire time taken, that is L2 miss penalty. Okay, so what is L1 miss penalty? We found that L1 miss penalty means when there is a L1 miss, then the entire extra time taken, that is L1 miss penalty. So let's use this concept. We are going to create this average memory access time formula recursively. Whenever there is multi-level cases, then you can write this average memory access time formula recursively. That is the best way to write average memory access time. This way you can also understand what is happening here, what is happening in the multi-level case, that also you can understand. Okay, so we are going to write this recursively. Okay, so let me write it here, that average memory access time formula when there is multi-level cache, then hint, let me tell you the hint is write average memory access time formula recursively. What do I mean by recursively? Let me explain. Very simple. The average memory access time seen by the CPU, that will be equal to, for every memory request we will always access L1 cache. Yes or no? There is a guarantee that for every memory request we will always access the L1 cache to check whether there is a L1 hit or a miss. Okay, so I can say that average memory access time that will be equal to L1 hit time, or I can say L1 access time. Yes or no? L1 hit time plus, because remember, for every memory request generated by the CPU, we will always access, first we will always access the L1 cache. We will check whether there is a hit or miss here. Okay. Now, when we will pay the penalty, L1 miss penalty, that we will pay only for L1 miss rate. When there is a miss in the L1 cache, then we have to pay the penalty. So you can see that the average memory access time seen by the CPU, that will be equal to, for every memory request generated by the CPU, first we will access the L1 cache memory to check whether there is a hit or a miss. So you can see for every memory request, this much time we always have to spend. So I can say this much time plus how much extra time we have to spend. Extra time we will spend only when there is L1 miss. So I can say that L1 miss rate multiplied by how much extra time we will spend. Can anyone tell me? When there is L1 miss, then we will spend some extra time, and that extra time, that is defined as L1 miss penalty. I told you, when there is a L1 miss, then after the detection of L1 miss, the entire time taken, the entire extra time, the entire additional time, that is called L1 miss penalty. So I can say that when there is a miss in the L1 miss rate into L1 miss penalty. Yes or no? Very simple. So this is your formula. That's it. That's it. Now here remember, this data is fine. This is L1 cache access time. This is now remember, this data we already know. L1 hit time, or this is called L1 access time. L1 cache memory access time. This miss rate, that is also fine. Now what is this L1 miss penalty? This again we can write recursively. So remember, this average memory access time formula we have seen, but what is this L1 miss penalty? Let me write. So let me write this L1 miss penalty, what this will be. Let's write the formula for L1 miss penalty. Remember, after the detection of L1 miss, we always have to access the L2 cache. Agree with me? So what is this L1 miss penalty? That is, after the detection of L1 miss, the entire extra time taken, the entire additional time taken, that is called L1 miss penalty. So after the detection of L1 miss, we always have to access the L2 cache to check whether there is a hit or miss. Okay, so I can say that this L1 miss penalty is equal to, for every L1 miss, first we will always access the L2 cache to check whether there is a hit or a miss. So I can say L1 miss penalty is equal to L2 hit time. Remember what is L2 hit time? This is basically L2 cache access time. Hit time or access time, we use them interchangeably. For cache memory, hit time or cache memory access time, these words we use interchangeably. So you can see this L1 miss penalty, this is equal to L2 hit time, because for every L1 miss, first we will always access the L2 cache to check whether there is a hit or a miss. And the, and when there is a miss in the L2 cache, means L2 miss rate multiplied by L2 miss rate multiplied by when there is a miss in the L2 cache, then we have to pay L2 miss penalty. Yes or no? Then we have to pay L2 miss penalty, because remember, after the detection of L2 miss, the entire additional time taken, that is called L2 miss penalty. So I can say that L2 miss rate multiplied by L2 miss penalty. Now let's again focus on this L2 miss penalty. What this L2 miss penalty will be? L2 miss penalty, that simply means after the detection of L2 miss, the entire additional time taken, that is called L2 miss penalty. So when there is a L2 miss, then we will always access the L3 cache. Okay, L2 miss, after L2 miss, we will always access, first we will always access L3 cache to check whether there is a hit or a miss. And when there is a miss in the L3 cache, then we will access the main memory. So here I can say that this L2 miss penalty, this is equal to L3 hit time, or I can say L3 access time. Yes or no? Because after the detection of L2 miss, we will always access L3 cache first to check whether there is a hit or a miss. So I can say for every L2 miss, this much time we always have to spend. That is L3 cache access time, or I can say L3 hit time. And when there is a miss in the L3, when there is a miss in L3 means L3 miss rate, then we have to pay L3 miss penalty. Okay, yes or no? So I can say then we have to pay L3 miss penalty. Now let's focus on this L3 miss penalty. What is this L3 miss penalty? What is the formula for L3 miss penalty? Remember, L3 is the last level cache memory. For the last level cache memory, the miss penalty is same as main memory access time, because main memory is the last level of memory hierarchy. So you can see when there is a miss in the L3 cache, then we will access the main memory. That's it. Yes or no? So you can see that this L3 miss penalty, that is same as main memory access time. Here you can stop. This will be same as main memory access time. Okay, so that's it. This is your average memory access time formula when we have multi-level caches. So we can write this recursively. I hope you understood this. This is a very simple formula. Did you understand? Please tell me. We are writing this recursively. Please understand. What is this L1 miss penalty? Just understand this concept. L1 miss penalty means after the detection of L1 miss, the entire additional time taken, that is L1 miss penalty. So I can say average memory access time is equal to, for every CPU memory request, we will always, for every memory request generated by the CPU, we will always access the L1 cache to check whether there is a hit or a miss. So this time we need to always spend, for every memory request generated by the CPU, this L1 access time, or I can say this L1 hit time, we always have to spend. So I can say this L1 hit time plus, when there is a miss in the L1, that is L1 miss rate multiplied by, then the entire extra time taken, the entire additional time taken to access, that is called L1 miss penalty. So you can see the formula is actually very simple. L1 hit time plus L1 miss rate into L1 miss penalty. But this L1 miss penalty we can write recursively. What will be L1 miss penalty? After the detection of L1 miss, the entire extra time taken, that is L1 miss penalty. And when there is a miss in the L1 case, then first we will always access the L2 case. For every L1 miss, first we will always access the L2 case to check whether there is a hit or a miss. So you can see this L1 miss penalty is equal to, for every L1 miss, we always have to spend this much time first. That is L2 hit time, or I can say L2 access time. And when there is a L2 miss, then we have to spend L2 miss penalty. Similarly, L2 miss penalty is equal to, for every L2 miss, we always have to spend this much time. That is L3 hit time, or I can say L3 access time. But when there is a L3 miss, then we have to pay the penalty, L3 miss penalty. And because this L3, this is the last level cache, so I can say L3 miss penalty is equal to main memory access time. So recursively, we can write the formula of average memory access time when we have multi-level caches. I hope you understood. Now let me discuss a very important note, that is these miss rate that we have used in this formula of average memory access time when we have multi-level caches. Then these miss rate that we have used, this L1 miss rate, L2 miss rate, L3 miss rate, all these miss rate that we have used, these are actually local miss rate. Okay, let me tell you, in the next lecture we will study this concept. Basically, when we have multi-level caches, then there is global miss rate, there is local miss rate. Okay, for every cache level, for every level of cache memory, we have two type of miss rate. We define two type of miss rate: local miss rate, global miss rate. Okay, you can see global miss rate and local miss rate. These concepts we will discuss in detail in the next lecture, but just giving you some idea that when we have multi-level caches like L1 cache, L2 cache, L3 cache, and so on. So for every level, we define two type of miss rate: global miss rate, local miss rate. And in this formula that we have seen, this previous average memory access time formula that we have seen, here all the miss rate that we have used, this L1 miss rate, this L2 miss rate, this L3 miss rate, all these miss rate that we have used, these are basically local miss rate. So in the question, if they mention that these miss rate are, in the question if local miss rate are given, you can use them directly. But if global miss rate is given, then you have to convert the global miss rate to local miss rate. And if nothing is given, they just mention the word miss rate. They don't mention it is local miss rate or global miss rate. If they just mention miss rate, then it is always by default local miss rate. And in this previous average memory access time formula, we always use the local miss rate. Okay, is this clear? But don't worry, this concept we will discuss in the next lecture. We will discuss what is global miss rate, what is local miss rate, and how to convert global miss rate to local miss rate, local miss rate to global miss rate. All these concepts we will study in detail in next lecture. Right now you don't have to worry. Okay, so I hope you understood this point, that after the next lecture, it will become very clear what I mean by this important note. In this note, I am saying that the previous average memory access time formula that we have seen for multi-level cases, all the miss rates that I have used, L1 miss rate, L2 miss rate, L3 miss rate, for every cache level, the miss rate that we have used, that is basically local miss rate of that level. Okay. And the definition of local miss rate, global miss rate, these we will discuss in the next lecture. Okay, don't worry right now. So you can see we will study and understand this in detail in the next lecture. Right now you don't have to worry. So that's it. We have seen the average memory access time formula for multi-level cases. You can see this screenshot is taken from computer architecture book by IIT Delhi professor Samruti Sarangi. You can see here, when we have L1 L2 cache, means two level cache memory we have, then average memory access time that will be equal to L1 hit time plus L1 miss rate into L1 miss penalty. But remember, this L1 miss penalty we can write recursively. What will be L1 miss penalty? That will be equal to L2 hit time plus L2 miss rate into L2 miss penalty. And because this L2 case, this is the last level case, so L2 miss penalty that is same as main memory access time. You can see L2 miss penalty is same as main memory access time. Okay, I hope you understood. So remember, when we have two level cache memory, then this will be our average memory access time formula, and this we can write recursively. You can see first we can write this formula, that average memory access time that is equal to L1 hit time, that is same as L1 access time. I can say L1 cache access time, and when there is a miss in the L1, then I can say miss rate of L1 into L1 miss penalty. And what is L1 miss penalty? That is L2 hit time, or I can say L2 cache access time, plus when there is a miss in L2, then L2 miss penalty. And for the last level cache, that is L2 cache memory, for that the miss penalty is same as main memory access time. Okay, so you can read this, everything we have already seen. So this is the average memory access time formula when we have multi-level cases. I hope you understood. Okay, you can see recursively we can write the complete formula. You can write recursively in this diagram. In this equation you can see here, average memory access time that is equal to L1 hit time plus L1 miss rate into L1 miss penalty. That's it, this is your formula. But now what is this L1 miss penalty? That is equal to L2 hit time plus L2 miss rate into L2 miss penalty. That's it. Now remember, what is this L2 miss penalty? That is L3 hit time plus L3 miss rate into L3 miss penalty, and so on. Okay, and so on. You keep going. And remember, for the last level, the miss penalty is same as main memory access time. And remember, in this formula, in this average memory access time formula for multi-level cases, all the miss rate that we have used for every level, for every case level, the miss rate that we have used, L1 miss rate, L2 miss rate, L3 miss rate, all these miss rate that we have used, that is basically local miss rate. Okay, and this we will discuss in the next lecture. What is local miss rate, what is global miss rate, this complete discussion we will do in the next lecture. But this is just an important point. In after the next lecture, you will understand that in this formula, this miss rate for every level, that is basically local miss rate, that is not global miss rate. Okay, so we have seen that when there is a cache memory hierarchy, or I can say when we have multi-level caches, then this average memory access time formula we can write recursively. Okay, this you can see basically this is the simple formula, L1 access time plus L1 miss rate into L1 miss penalty. Now this L1 miss penalty we can again write. Okay, then this L2 miss penalty we can write. So recursively we can go. Okay, and remember, for the last level cache memory, the miss penalty that is equal to main memory access time. Okay, so this we have already seen. I hope you understood the concept. You understand, you don't have to remember the formula, you just have to understand the concept, then you can write the formula on your own. Okay, nothing hard here. Now let's see another way of writing the average memory access time formula when we have multi-level cases. Let's assume we have two level cases, L1 L2, and after that there is main memory. So in the memory hierarchy, the last level is basically main memory. Okay, so let's see what will be the average memory access time formula. One one way of writing this formula that we have already seen. Now let's see another way of writing average memory access time formula. So what is that? So what is the first step? That is CPU will generate the memory request. Now after that, there are two possibility. Either there will be L1 hit or L1 miss, because after CPU will generate the memory request, first we will go to the L1 cache. We will check the L1 cache if there is a hit or a miss. So you can see there are two possibilities. Either there is a L1 hit or there is a L1 miss. Okay, so let me say that here I can say either there is a L1 hit or there is a L1 miss. Tell me, if there is a L1 hit, then what is the total access time seen by the CPU? the total access time seen by the CPU when there is a L1 hit, that is same as L1 access time. Yes or no? So remember, when there is a L1 hit, then the total access time seen by the CPU, that is same as L1 hit time, or I can say L1 access time. So I can say that will be L1 access time, or this you can also say this is basically, or you can say this is basically L1 hit time. Okay, very simple. This is the total access time seen by the CPU when this memory request is available in the L1 cache memory. Very simple. But if this memory request is not available in the L1, it means there is a L1 miss. When there is a L1 miss, then what are the possibilities? When there is a L1 miss, now again there are two possibilities. If there is a L1 miss, either it will be L1 hit, either it will be L2 hit, because when there is a L because when there is a L1 miss, then we will go and we will check in the L2 case whether there is a L2 hit or a L2 miss. So you can see either there will be L2 hit or there will be a L2 miss. Correct? Now, if there is a L2 hit, then what is the total access time seen by the CPU? Can you tell me? What is the total access time seen by the CPU when there is L1 miss and L2 hit? So that is same as L1 access time plus L2 access time. Yes or no? Because remember, for every memory request, first we will always check the L1 cache. So I can say L1 access time. And because there is a L1 miss, so we will access the L2 cache. So that is L2 access time. But because there is a L2 hit, so no extra time we have to spend. So I can say when there is L2 hit and L1 miss, then what is the total access time seen by the CPU? That will be L1 hit time plus L2 hit time. Or I can say L1 access time plus L2 access time. I can say TL1 plus TL2. Okay, understand what this means? This means TL1 means L1 access time. Okay, this TL1, this is simply L1 access time, or you can say L1 hit time. L1 hit time. Very simple. Now, when there is a L2 miss, then what is the total? Now, when there is a L2 miss, then what is the total access time seen by the CPU when there is a L2 miss? When there is a L2 miss, then we have to access the main memory. So you can see in this situation, when there is a L1 miss, L2 miss, in this situation, what is the total access time seen by the CPU? That will be equal to L1 access time plus L2 access time plus main memory access time. Okay, agree? So very simple. From this tree diagram we can convert into a formula. So we will get another way of writing the average memory access time formula. Remember, this another way of writing this average memory access time formula. This is same as the previous formula that we have seen. If you simplify this formula, then you will get the same previous formula. But this is just another way of writing average memory access time formula. Very simple. Very simple. When the CPU will generate the memory request, then first we will always go to the L1 cache. We will check in the L1 cache whether there is a hit or a miss. Now, there are two possibilities: if there is a L1 hit or if there is a L1 miss. If there is a L1 hit, then the total access time seen by the CPU, that is same as L1 access time, or I can say L1 hit time. But if there is a L1 miss, then there are two possibilities. Because when there is a L1 miss, we will always go to the L2 cache. In the L2 cache, we will check whether there is a hit or a miss. So there are two possibilities: L2 hit, L2 miss. If there is a L2 hit, then what is the total access time seen by the CPU? That is L1 access time plus L2 access time. But when there is a L2 miss, then we have to access the main memory. So in this situation, what is the total access time seen by the CPU? That will be L1 access time plus L2 access time plus main memory access time. So this tree diagram, let's convert into a formula. That will be another way of writing average memory access time formula. What is that? That is hit rate of L1. I can say L1 hit rate multiplied by L1 access time. You can see L1 hit rate multiplied by L1 hit time, or I can say L1 access time, I can say TL1 plus this. Because remember, you can see in this tree diagram, you can see L1 hit rate when there is L1 hit. So I can say L1 hit rate multiplied by L1 access time plus when there is L1 miss, then what will happen? When there is L1 miss, then what will happen? Either we have this path or we have this path. So you can see when we have L1 miss, L2 hit, then this is the total access time seen by the CPU. So I can say plus L1 miss rate into L2 hit rate into L1 access time plus L2 access time. Yes or no? Because you can see in this tree diagram, you can see if there is a L1 miss, then either there can be L2 hit or there can be L2 miss. So you can see when there is L1 miss and L2 hit, then this is the total access time seen by the CPU. That will be access time of L1 plus access time of L2. So this is what I've written: L1 miss rate into L2 hit rate into access time of L1 plus access time of L2 plus this path. When there is L1 miss and L2 miss, then this is the total access time seen by the CPU. So you can see L1 miss rate multiplied by L2 miss rate multiplied by access time of L1, L2 access time plus main memory access time. Okay, that's it. This is another way of writing average memory access time formula. But let me tell you, if you simplify this formula, again you will get the same previous formula. So remember, if after simplification of this formula you are getting the previous formula, then always use the previous formula. This is my suggestion to everyone. Okay, so please understand the two formula that we have seen, among them always use the first formula. Okay, when we have multi-level cases, then to save calculation time, use this formula. Which formula? The first formula that we have seen. Because remember, the second formula and first formula, they are same. If you simplify the second formula, you will get the first formula. So please understand that to save the calculation time, always use this first formula, that is average memory access time is equal to, if you have two levels of cache memory L1 L2, then this average memory access time formula, that will be equal to L1 access time, L1 access time plus when there is miss in the L1 miss rate into L1 miss penalty. And what is this L1 miss penalty? L1 miss penalty, that will be equal to L2 access time plus when there is L2 miss rate, then L2 miss penalty. And because this L2 is the last level cache, so what will be this L2 miss penalty? This will be same as main memory access time, because this is the last level of cache memory. So this will be main memory access time. That's it. So this is the formula you have to use every time to save calculation time. Of course, if you want, you can use the another way of writing the same formula. But let me tell you, when you do the calculation, that another way of writing this average memory access time formula, that will take a lot of time. Because when you simplify that formula, then you will get this formula. Okay. So that is the reason, to save calculation time, always use this formula. I hope you understood this. Let's solve this question from University of Minnesota. The L3 cache of a computer has hit time of 15 cycles. So L3 cache hit time is 15 cycles. What it means? It simply means L3 cache access time, that is 15 cycles. And miss penalty is 300 cycles. Suppose the hit rate for this cache, for this L3 cache, the hit rate for a given application, for a given program is 95%. Considering just this case, see, this is an interesting statement. This question is saying that considering just this case means in your system you only have L3 cache, no other cache memory you have. So, is this multi-level cache structure or is this single level cache structure? Let me know. In this system, do we have single level cache or do we have multi-level cache? We have single level cache. Okay, so this is just an interesting question, that they are using the word L3 case. They are using this word, but now they are saying that considering just this case, cache memory, what is the average memory access time in cycles? Recall that average memory access time, that is equal to hit time plus miss rate into miss penalty. This formula we have already seen in the previous lecture when we were discussing average memory access time for single level cache structure. So you can see, suppose we can improve the hit rate of the application to 98%. From 95 to 98, we can improve the hit rate. In this situation, what will be the new average memory access time? So basically, there are two questions here. Let's solve both of them. So let me say that this is basically part 2 and this is part 1. Okay, so let's solve both of them. So let's solve the part 1 in this question, D part 1. So this is very simple. We only have single level cache memory because this L3 cache, this is the only cache that we have in the system. So single level cache memory we have. So what will be the average memory access time? So you can see average memory access time, that will be equal to cache memory hit time, or I can say cache memory access time. So cache memory hit time, that is basically 15 cycles. So I can say we have 15 cycles plus miss rate. Hit rate is 95%, so the miss rate is 5%, yes or no? And 5% when you convert into fraction, so you divide by 100. So basically miss rate is 0.05. This is the miss rate. Miss rate into miss penalty. What are the miss penalty? You can see miss penalty is 300 cycles. This is the miss penalty. So very simple. Cache memory access time, that is 15 cycles. Cache memory miss rate, that is 0.05. And cache memory miss penalty, that is 300 cycles. And average memory access time, that is equal to cache memory access time plus miss rate into miss penalty. Okay, this formula we have already seen in the previous lecture. So let's see here. The answer will be 15 into this double zero will cancel, so it will become 15, so that will become 30. So you can see 30 cycles. So the average memory access time, when you calculate that, you will get 50. So when you calculate average memory access time, then you will get 30 cycles. Very simple. Now let's see the second part. The question is saying, suppose we can improve the hit rate from 95% to 98%. So now the new miss rate, that is basically 0.02. Remember, miss rate will be 2%. So if you want to convert to fraction, then you divide by 100. So don't make this mistake that 2% miss rate, don't write it 0.2. This is a silly mistake that you can make. This is a common silly mistake. Okay, please understand that 2% miss rate, if you want to convert into fraction, then you divide by 100. So it will be 0.02. And when you want to convert this fraction to percentage, then you multiply by 100. So don't make this silly mistake that you are writing this miss rate 2% as 0.2. No, it will be 0.02. So let's see the part 2, D part 2. Average memory access time, AMAT, that will be equal to cache memory hit time, that is 15 cycles. We have improved only the hit rate. Nothing else has changed. Yes or no? So I can say the cache memory hit time, that is 15 cycles plus now the miss rate, that is 0.02 into the miss penalty, that is 300. So here you can see this will be 15 plus 6. This will be 21 cycles. One interesting thing, did you notice? What is the interesting thing here? The interesting thing is, with 95% hit rate, we are getting average memory access time equal to 30 cycles. You can see 30 cycles, this is the average memory access time with 95% hit rate. Okay. Now remember, we have increased, or I can say we have improved the hit rate only by 3%, not by much. From 95, we have made it 98%. We have improved the hit rate from 95 to 98%. So only 3% of increase we have done in the hit rate. But how much increase has happened in the average memory access time? They can also ask you this. This is an interesting question. Can you tell me the percentage improved, the percentage improvement in average memory access time? There is a 3% improvement in the hit rate. So tell me, what is the percentage improvement in the average memory access time? So the percentage improvement in the average memory access time, that will be equal to the difference. You can see the improvement is basically 9 cycles. So I can say 9 divided by the original, I can say the old, that is 30 multiplied by 100. So that will be equal to 30%. So this is another very good question. In the GATE exam, they can ask you this question that first we have 95% hit rate, then we have improved the hit rate by 3%. then what is the percentage improvement in the average memory access time? So that will be 30%. This is very interesting, right? So when you improve the hit rate even by 1%, 2%, 3%, then also the improvement in the average memory access time will be huge. I hope you understood this. So this is the answer given for the previous question. Now let's solve this question. Effective access time example. A computer has single level cache of chip with 2 nanosecond hit time and 98% hit rate. Main memory access time is 40 nanosecond access time. What is computer's effective access time? Okay. Now there is a second part. If we add on chip cache with 0.5 nanosecond hit time and 94% hit rate, what is the computer's effective access time now? And what is the speed up we have got? And what is the speed up does the on chip cache gives to the computer? Okay, so basically there are three questions in this. So basically there are three parts in this question. So let's solve this question. Let's solve the first part. The first part is saying that we have computer with single level cache memory, and this is a off chip, means this is not on the processor chip. We have a single level cache memory, but this is not on the processor chip. This is off chip with 2 nanosecond hit time. So this is the cache memory access time, 2 nanosecond, hit rate 98%, and main memory access time, that is 40 nanosecond. So what will be the average memory access time? Computer's effective access time. Remember this effective access time I told you, this is also called average memory access time. This is another name for average memory access time. So what will be average memory access time? That will be equal to cache memory access time, that is 2 nanosecond. I can say cache memory access time, or I can say cache memory hit time, plus miss rate. What is the miss rate? The hit rate is 98%, so the miss rate will be 2%, that is 0.02. This is the miss rate into miss penalty. When we have single level cache memory, then the miss penalty is very simple, that is main memory access time. So that is 40 nanosecond. So you can calculate this 2 plus. So we can calculate this. This will be 2 plus 0.8. So that will be 2.8. 2.8 nanosecond. This is the average memory access time. Now let's see the second part of this question. Now the question is saying that if we add on chip cache memory in this system, now we have added on chip cache memory. So tell me one thing, this new cache memory that we have added, will this be level 1 or level 2? Already we have a off chip cache. Let me call this off chip cache for a moment. Let me call this cache A, and this new on chip cache that I'm adding, let me call this cache B. So tell me, in this second part of the question, we have added on chip cache. So this new cache, will it be level 2 or level 1? This will be level 1, not level 2, because this is on chip, means this is on the processor chip. This is closer to the CPU. The cache memory which is closest to CPU, that is called primary cache, or I can say L1 cache. So please understand that in the second part of the question, in the second part, we have CPU and this new cache memory, that is on chip cache. Okay, yes or no? You can see this new cache, or I can say the on chip cache, that is your L1 cache. That will be called L1. And this old off chip cache, that will become L2. So you can see this old cache, off chip cache, that will be called L2. And of course, then there is main memory. So in this question, one mistake you can make, that the new cache memory that is added, you may consider this as level 2, and you may consider that the old cache memory is level 1. No, please understand that off chip means this is not on the processor chip, on chip means this is on the processor chip. So on the processor chip means this new cache memory, this is closer to the CPU, so this will be your primary cache, or I can say L1 cache. So please understand, this cache B, this will become the L1 cache, this cache A, this will become the L2 cache. Okay, now this has become multi-level cache memory. So you can see here we have added this on chip cache with 0.5 nanosecond hit time and 94% hit rate. Now what is the average memory access time? So let's calculate the average memory access time. When we have multi-level cache memory, then this average memory access time we can calculate recursively. So you can see the average memory access time that will be equal to L1 hit time plus L1 miss rate into L1 miss penalty. So you can see what is L1 hit time, that is 0.5 nanosecond. So you can see this is the L1 hit time plus L1 miss rate. The L1 hit rate that is 94%. So the L1 miss rate that will be 6%. 6% means 0.06. This is the L1 miss rate into L1 miss penalty. Now what is L1 miss penalty? This L1 miss penalty that will be equal to L2 hit time plus L2 miss rate into L2 miss penalty. Yes or no? So you can easily see this L1 miss penalty. What I can say, this will be L2 hit time. What is L2 hit time? That is 2 nanosecond. You can see the L2 hit time that is basically 2 nanosecond plus L2 miss rate. L2 miss rate is basically 2%. So I can say 0.02. That is the L2 miss rate into L2 miss penalty. Because L2 is the last level case, so for L2 the miss penalty is same as main memory access time, and main memory access time that is basically 40 nanosecond. Okay, so very simple. Now you can easily calculate the average memory access time for this multi-level cache, two level cache memory. You can see that will be zero point 0.5 plus 0.06 multiplied by 2 plus 0.02 into 40. This we have already calculated. This was 2.8. So I can put this here 2.8. And now we can calculate what will become this average memory access time. So when you calculate, then you will get average memory access time equal to 0.668. This is in the nanosecond. So this is the average memory access time. Now there is a third part of this question. The question is asking what is the speed up, how much speed up we got. So remember, you can see the old average memory access time that was 2.8 nanosecond. The new average memory access time that is 0.668 nanosecond. So what are the speed up we got? Let me tell you about speed up. How to calculate speed up? This is very simple. If system A has execution time Ta and system B has execution time Tb, then if the question asks you speed up of system B over system A, then that will be equal to execution time of system A divided by execution time of system B. So please understand, if I ask you what is the speed up of system B over system A, then on the numerator you will write the execution time of system A. Okay, the execution time of system A, or I can say TA. TA divided by TB. Is this clear? So if I ask you what is the speed up of system B over system A, then that will be TA divided by TB. And if I ask you what is the speed up of system A over system B, then on the numerator you will write TB, on the denominator you will write TA. Is this point clear? Let me know. So if I ask you speed up of system B over system A, then that will be execution time of system A divided by execution time of system B. And if I ask you speed up of system A over system B, then that will be execution time of system B divided by execution time of system A. Okay. This concept of speed up we also study in the pipeline. When we study pipeline concepts, there also this same concept we have already seen. Okay. But don't worry, I have again provided you. But don't worry, we have done the revision of the speed up formula. You can see, if we want to find the speed up of system B over system A, then that will be execution time of system A divided by execution time of system B. So here you can see in this question, we want how much speed up we got when we are using the on chip. So we are basically finding the speed up by the new system over the old system. Yes or no? So you can see this speed up that we need to find. This is the speed up by the new system over the old system. Yes or no? Speed up by new system over old system. Okay, so you can easily see speed up of this new system over old system, that will be execution time of old system divided by execution time of new system. So you can see the average memory access time of the old system, that is 2.8 nanosecond, divided by the average memory access time of the new system, that is 0.668. So you can calculate this value, that will become the speed up. You can see here the speed up is basically 2.8 divided by 0.668, so that will be 4.2. So the speed up, that will be 4.2. This will be the speed up. This is the answer. Let's solve this NILET exam question. A computer has single cache of chip with 3 nanosecond hit time and 95% hit rate. Main memory has 50 nanosecond access time. If we add on chip cache memory with 0.6 nanosecond hit time and 98% hit rate, then what is the computer's effective access time? Effective access time means average memory access time. These are alternatively used. You can call it effective access time, effective memory access time, or expected memory access time, or average memory access time. All these things are same. So let's see what will be the answer for this. This is a multi-level cache, because initially we have single level cache, that is off chip, that is off the processor chip, that is not on the processor chip. So this off chip cache, for a moment let me call it cache A. Let me call it cache A. Now we are adding a on chip cache. Let me call it cache B. Just tell me a simple point. Initially we have only one level cache memory, only one cache memory we have, that is cache A, and that is off chip, means that is not on the processor chip. Now we are adding a new cache memory, that is on chip, on the processor chip. So tell me, in this new design, after adding this on chip cache, which of them will be L1, which of them will be L2, which of them will be L1 cache, which of them will be L2 cache? Remember, the cache memory which is closer to CPU, that is your L1 cache. So you can see this cache B, this is on chip cache, means this is on the processor chip. So this is closest to CPU. So this will be called L1 cache. Please understand, this will become the L1 cache, or I can say primary cache, or I can say upper level cache. You can say this will become your primary cache, or you can say this will become your upper level cache, or you can say this will become your level 1 cache, L1 cache. And this cache A, this off chip cache, this will become your L2 cache. Okay, very simple. In this question, the silly mistake students can make, that is, they will think that initially the first cache memory that we have, that is L1, and the newly added cache memory, that will be L2. This is a mistake, please understand, because this newly added cache memory, this is on chip, means this is on the processor chip, this is closest to CPU, so this will be called L1 cache. The cache memory which is closest to CPU, that is your primary cache, or I can say L1 cache. Now you can easily solve this question. This is multi-level cache memory. So you can see we have CPU here, then there is this on chip cache, and then there is off chip cache, and then there is main memory. Now we can easily calculate what will be the average memory access time formula. Average memory access time, that we can find recursively when we have multi-level cases. I told you, when you have multi-level cases, then the average memory access time, this formula you can write recursively. So average memory access time, that will be equal to the hit time of on-chip cache plus miss rate of on-chip cache multiplied by miss penalty of on-chip cache. So very simple. Let's call it L1, let's call it L2. So you can see that this average memory access time formula, what that will be, that will be basically L1 hit time, or I can say L1 access time plus L1 miss rate, L1 miss rate multiplied by L1 miss penalty. And also remember, what is this L1 miss penalty? That also we can write recursively. So you can see that L1 miss penalty, that will be equal to, that will be L2 hit time, or I can say L2 access time plus L2 miss rate into L2 miss penalty. Now, what will be L2 miss penalty? Because this is the last level of cache memory. So, for the last level of cache memory, the miss penalty is same as main memory access time. So, this will be main memory access time. So that's it. So remember, when we have multi-level cache memory, then we can write this average memory access time formula recursively. Okay, you can see this will be L1 hit time, or I can say L1 access time plus L1 miss rate into L1 miss penalty. This L1 miss penalty, again, we can write that will be L2 hit time, or I can say L2 access time plus L2 miss rate into L2 miss penalty. Remember, this L2 is the last level cache. So for the last level cache memory, the miss penalty is same as main memory access time. So that's it. You can just apply this formula. So the average memory access time, that will be equal to L1 hit time. What is L1 hit time, or I can say L1 access time? You can see the L1 hit time, that is basically 0.6 nanosecond. 0.6 nanosecond plus what is L1 miss rate? You can see the L1 hit rate is 98%. So the L1 miss rate, that will be 2%. That means 0.02 multiplied by L1 miss penalty. Now what is this L1 miss penalty? That will be equal to L2 hit time. What is L2 hit time? That is 3 nanosecond is the hit time for L2. So 3 nanosecond plus L2 miss rate. You can see the L2 hit rate, that is 95%. So the L2 miss rate will be 5%, or I can say 0.05. This is the miss rate of L2 multiplied by L2 miss penalty. But L2 is the last level case. So L2 miss penalty is same as main memory access time. Main memory access time, that is given to you 50 nanosecond. So that will be 50. Now you can just calculate and you can get your answer. So the average memory access time, that will become, tell me what it will become. Anyone calculated? Did you calculate? 0.71. Okay, that's it. So when you calculate this, you will get 0.71 nanosecond. This will be the average memory access time. That's it. So the answer will be option C, 0.7. Let's solve gatecse 2017 question. In two-level cache system, the access time of L1, L2 caches, these are 1 and 8 clock cycles. So L1 cache access time, that is 1 cycle. L2 cache access time, that is 8 cycles. The miss penalty from L2 cache to memory, L2 cache to main memory, that is 18 clock cycles. So basically this, because this L2 cache, this is the last level cache. So the miss penalty of L2 cache, that is basically main memory access time. So this 18 clock cycles, this is the main memory access time. The miss rate of L1 cache is twice of L2. The average memory access time of this cache system is 2 cycles. We need to find the miss rate of L1 and L2. So this is a very simple question. We just need to apply the average memory access time formula. You can see in this question, average memory access time is given to us, and we need to find the miss rate of L1, L2. So I can assume the miss rate, I can assume here this information is given that the miss rate of L1 is twice of L2. So what you can do, you can assume L2 miss rate, or you can assume L1 miss rate, anything. Okay, so let me assume that L2 miss rate, that is equal to capital M or a small m. So let me assume that L1, sorry. So let me assume this L2 miss rate, that is equal to small m. So what will be L1 miss rate? You can see the miss rate of L1, that is twice of L2. So the L1 miss rate, that will be equal to 2m. Correct? Okay, so this is what I've assumed. Now you can see the average memory access time. This is given in this question. So let's apply the average memory access time formula. When you have multi-level cache structure, then you can apply this average memory access time formula recursively. So average memory access time, that will be equal to the access time of L1 cache plus the miss rate of L1 cache into the miss penalty of L1. So you can see this miss rate of L1, that I've assumed, that is 2m. Okay, so this is the miss rate that we have assumed for L1 cache multiplied by the L1 miss penalty. Now what is this L1 miss penalty? This L1 miss penalty, this is simply L2 access time plus miss rate of L2. What is the miss rate of L2? Miss rate of L2, that is basically m multiplied by L2 miss penalty. Okay. Now you can see in this question, this L2 miss penalty is already given to us. This L2 is the last level cache. So for L2, the miss penalty is same as main memory access time. You can see this is already given to us. The miss penalty of L2 is given, that for L2 the miss penalty is basically 18 clock cycles. So you can see the L2 miss penalty, that is same as main memory access time, that is given to us 18 clock cycles. Okay, and this access time of L2, that is 8 clock cycles. This we also have. And this average memory access time, this is given to us, this is 2 cycles. So this value also is 2 cycle, we know this value. What is the access time of L1? That is 1 cycle. Access time of L1, that is 1 cycle. So we have everything, we just need to calculate the value of M. So you can see the equation that we got, that is equal to 2 equal to 1 plus 2M into multiplied by, inside what we have, inside we have 8 plus M into 18, or I can say 18M, correct? So let's simplify this. What we will get? We will get 1 equal to 16M plus 36M square. When we simplify this, we will get 1 equal to 16M plus 36M square. So we got a quadratic equation basically. So we got 36M square plus 16M minus 1 is equal to 0. So this quadratic equation we got, and from this quadratic equation we can find the value of M, that will be equal to, remember when we have ax square plus bx plus c equal to 0, when we have this quadratic equation, then if you want to find the root, means if you want to find the solution, or I can say the value of x, then that will be equal to minus b plus minus square root of b square minus 4ac divided by 2a. Okay, this is the formula to find the solutions from this quadratic equation. So you can see this is also a quadratic equation. So what will be the value of M? That will be equal to minus b, that is minus 16 plus minus square root b square minus 4ac, that is 16 square minus 4ac. So you can see 4a is 36, c is minus 1. Okay, yes or no? So this is divided by 2a. A is 36. So you can see the value of M, that will be equal to minus 16 plus minus square root of 16 square plus, because this minus and this minus, this will become plus, plus 36 into 4 divided by 72. So this will become minus 16 plus minus square root of 400 divided by 72. Now remember, this miss rate can never be negative. So you can easily see that you can remove this negative sign. Okay, because remember, there will be two values here when you take plus or when you take minus, but this miss rate can never be negative. Because it can never be negative, so I can say that this miss rate, that will be equal to M is equal to 20, and you can just take this plus sign. So you can see 20 minus 16. So I can say this will become 20 minus 16 divided by 72. So that will be 4 divided by 72. So what will be this value? The L1 miss rate is 0.11. The L2 miss rate, that is 0.055. So for this question, the answer will be option A. You can see the miss rate of L1, that is 2M, and that we have calculated, that is 0.11, and the miss rate of L2, that is 0.056. So you can see actually it will be 0.05555 like that. So we can write it 0.056. So for this question, the answer will be option A. Now let's discuss an important point, that is miss penalty definition by Karl Hemacher book. So you can see in the Karl Hemacher book, the miss penalty definition is given, that is we refer to the total access time seen by the processor when there is a miss as miss penalty. So when you read this statement, this is the definition of miss penalty given in the Karl Hemacher book. So can you remember, can you recall something that we have seen in the previous lecture? The total access time seen by the processor when the data is not in the cache memory, what we call it in the previous lecture, what we call it, or I can say what other authors call it. Other authors call it miss time. They don't call it miss penalty, they call it miss time. Yes or no? We have already seen in the previous lecture that most of the authors, majority of the authors, they call the total access time seen by the processor when the data, the requested data, the requested data is not in the cache memory, that is called miss time. Okay, but here you can see in Carl Hemacher book, this total access time seen by the processor when the data is not in the cache memory, that is called miss penalty. So I can say that according to Carl Hemacher, according to the definition of miss penalty by Carl Hemacher, the miss penalty also includes the time to check the cache memory for hit or miss. Yes or no? So this is the only difference. So I am just saying that the miss penalty definition by different authors can be different. But the miss penalty definition that we have seen so far in the previous lecture, that is most widely used in most of the books, in most of the standard books by most of the authors, they follow the miss penalty definition that we have seen in the previous lecture. Basically, the majority of the authors, they follow the miss penalty definition, that is the additional time after the detection of miss, the additional time to access, that is your miss penalty. That is most widely used definition of miss penalty that we have seen in the previous lecture. But I am just telling you that there are some authors, like for example Carl Hemacher, this is one of the author who uses different definition for miss penalty. You can see, according to Carl Hemacher book, the miss penalty definition is, we refer to the total access time seen by the processor when there is a miss as miss penalty. Actually, in the previous lecture we have seen this total access time seen by the processor when there is a miss, this is called miss time. Okay, so I can say that what we call miss time, Carl Hemacher is calling it miss penalty. And when I say we, who is we? Berkeley, Princeton, and majority of the resources. So the definition of miss time that we have seen, this is the this is the total access time seen by the processor when the requested data is not in the cache memory. That is called miss time. So you can see what we defined as cache miss time is called miss penalty in the Carl Hemacher book. So I can say that according to Carl Hemacher, the miss penalty also includes the time to check the cache memory for hit or a miss. Okay, this is the only difference I can say. Okay, so this important point I wanted to tell you, that sometimes it may happen that they can give you a different definition of miss penalty in the gate exam. Okay, in the gate question they can give you the miss penalty definition, they can give you, okay, they can mention what the meaning of miss penalty, and they can give you some other definition of miss penalty, so you have to take care. Okay, so remember, according to majority of the authors, the miss penalty does not include the time to check the cache memory for hit or a miss. So according to majority of the authors, the miss penalty is basically the additional time after the miss detection, the additional access time, that is the miss penalty according to majority of the authors. But according to some authors, like for example Carl Hemacher, the miss penalty also includes the time to check the cache memory for hit or miss. Okay, so I can say what we call miss time, what we defined miss time in the previous lecture, that is called miss penalty by Carl Hemacher. Okay, very simple. So you can see in the previous lecture, this is recap. In the previous lecture, we have seen the definition of miss time. What was miss time? Miss time is basically the total time seen by the CPU when there is a cache miss. And this miss time definition, this is used as miss penalty by Carl Hemacher. So remember, in the previous lecture, we have seen miss time is equal to miss penalty plus hit time. But now, according to Carl Hemacher definition of miss penalty, the miss penalty itself is same as miss time. Miss means miss penalty includes the cache memory hit time, the cache memory access time that is included in the miss penalty defined by Carl Hemacher. Okay, I hope you understood this point. So you can see in the previous lecture, these slides we have seen from the Berkeley University. You can see that what is miss time. Read this definition of miss time. Miss time is basically the total time spent. Miss time is basically the total time spent, or I can say total time seen by the processor when there is a miss, not just miss penalty. Means miss time is equal to miss penalty plus hit time. This we have already seen in the previous lecture. The same thing is given in the Princeton University. What is miss time, what is hit time? Basically, hit time means when the requested data is in the cache memory, then the total time to access, that is hit time. And when the requested data is not in the cache memory, then the total time to access, that is miss time. So you can see the miss time definition that we have seen in the previous lecture, that is used as miss penalty definition in the Carl Hemmecher book. This is the only thing I just wanted to tell you. This is an important note, that in the gate exam question, you focus, if the definition of miss penalty is given to you, then you focus on those words. What is the meaning of miss penalty given to you? You focus on those words, and then you you determine which definition they are using, and then you determine the meaning of miss penalty. Okay, but remember, if they just mention the miss penalty word, they do not define it, they do not give you extra information about the miss penalty word, then you can uh, um, then you can use our previous definition. In the previous lecture, the definition that we have seen, you can use that definition, because that is followed by majority of the authors, also by the Patterson and Hennessy. That is the most standard book for computer architecture, and that book also follows that definition. Okay, most of the time we are going to follow Patterson and Hennessy book. Okay, so let me tell you a note here. In the previous lecture, we have seen the miss penalty definition by Patterson. In the previous lecture, we have seen the miss penalty definition by Patterson and Hennessy book. That is, miss penalty was basically the penalty of miss. Means, after the miss detection, after cache miss has been detected, after that, the whole additional time taken, the additional time required to access, that is called miss penalty. Okay, so you can see the majority of the computer architecture books and the university courses and the NPTEL courses, they follow Patterson and Hennessy book. So let me tell you, this is the most standard book. This is the most followed book for computer architecture. So that is the reason we are also going to follow this Patterson and Hennessy book by default. Okay. So let me give you the final conclusion. You might be confused because you have seen two definitions of miss penalty. One definition according to Carl Hemmecher, another definition according to Patterson and Hennessy. So you might be confused what to consider. So let me tell you, majority of the resources define miss penalty as the additional time required for an access in the event of a miss. Means, majority of the resources, they follow the definition given in Patterson and Hennessy. Okay, so that is what we are going to follow. We are, by default, we are going to consider that miss penalty, that is basically the additional time required when there is a miss, when there is a cache miss, then after the detection of cache miss, what are the additional time required to access, that is your miss penalty. So remember, by default, we are going to follow the Patterson and Hennessy book, and we are going to consider that miss penalty does not include the time to check the cache memory for hit or a miss. Okay, after the hit or a miss detection, I can say, after after the miss detection, the entire additional time taken to access, that is your miss penalty. And you can see Carl Hemmecher definition of miss penalty, it includes the time to check the cache memory. Means, the miss penalty definition by Carl Hemmecher, that includes the hit time, the cache hit time, the cache memory hit time is included. Okay, and let me tell you, we will follow what majority of the resources follow, unless in the question it explicitly says that miss penalty includes the time to check the cache memory. See, if the gate exam question says that miss penalty includes the time to check the cache memory, then immediately what will come to your mind? The Carl Hemmecher definition will come to your mind. Yes or no? In the gate exam, in the question, if they explicitly say that miss penalty includes the time to check the cache memory for hit or a miss, then what we are going to assume? Then we are going to assume the Carl Hemmecher definition of miss penalty. Okay, but if they just use the miss penalty word and they do not define it, they do not give you extra information about the miss penalty, then by default we are going to assume that this is the additional time taken after the miss detection, the additional time to access, that is your miss penalty. Okay, so I hope this confusion is clear now. Let me tell you, you might be confused right now because you have seen miss penalty, two definitions you have seen. In one definition, which majority of the resources follow, in that definition, miss penalty does not include the time to check the cache memory for hit or a miss. Okay, means miss penalty is basically the additional time after the miss detection, the additional time to access, that is the miss penalty. This is the definition followed by majority of the resources, and this is what we will follow by default, and this is what gate follows by default. In all the gate questions, by default, this Patterson and Hennessy definition is followed for miss penalty. But in the gate exam question, if explicitly it is given that miss penalty includes the time to check the cache memory, then you will imagine, you will assume the Karl Hemmecher definition of miss penalty. So there is no confusion here. Please understand. Now I am going to solve many questions from the standard university and also from the gate exam. And after solving these questions, it will become very clear to you that there is no confusion. Okay, you will never get confused in the definition of miss penalty, because back to back many questions I will solve, and in all those questions you yourself will tell me whether miss penalty includes the time to access the cache memory or not, because that will be given in the question, that information will be given in the question. Okay, so do not worry, in the question every information will be given. There is nothing, there is no ambiguity, there is nothing, there is no ambiguity, and there is nothing to worry. Okay, but let's discuss this miss penalty definition by Karl Hemmecher. So we have seen that what we defined as miss, so you can see what we defined as miss time in the previous lecture, that is called miss penalty by Karl Hemmecher. So you tell me what will be average memory access time formula as per, as per, so you tell me what will be average memory access time formula as per Karl Hemmecher definition of miss penalty. Means for a moment assume that in the gate question, in the exam question, it is given explicitly, it is written that miss penalty includes the time to check the cache memory. Now can you tell me what will be the average memory access time formula? Let me know. So let's see the average memory access time formula according to Karl Hemmecher. Very simple. See, remember the average memory access time formula we have already seen in the previous lecture in terms of hit time and miss time. If you remember, what was that? That was cache hit rate into cache hit time plus cache miss rate into cache miss time. Okay, yes or no? So you can see this we have already seen that cache hit rate. So this we have already seen that cache hit rate. Let me call it H. H means this is the cache memory hit rate. So cache hit rate multiplied by cache memory access time plus cache memory access time means this is the hit time. So I can say hit rate into cache memory hit time plus miss rate into miss time. What is miss rate? That is 1 minus h into miss time, into miss time. This formula we have already seen in the previous lecture. But remember, this miss time, according to Karl Hemmecher, this is miss penalty. Yes or no? According to Karl Hemmecher book, the miss penalty includes the time to check the cache memory for hit or miss. So you can see what we are calling it. So you can see what we called miss time, that is called miss penalty. That is called miss penalty by Karl Hemmecher. Okay. So what you can see, this you can replace with miss penalty. Okay, because I am seeing the average memory access time formula according to Karl Hemmecher. So I can say this average memory access time, this is equal to H into TC, means hit rate into hit time plus 1 minus H. And you can see this multiplied by miss penalty. Okay, yes or no? Miss penalty. So that's it. This is the formula if we follow the miss penalty definition by Karl Hemmecher. So please understand, this formula we will apply only if it is given in the question that miss penalty includes the time to check the cache memory. then we will apply this formula, otherwise we will not apply this formula. I hope you understood this point. Okay, very simple. The same formula we can get logically also, because remember, initially the CPU will generate the memory request. Now when the CPU has generated memory request, first we will go to the cache memory. Either there will be hit or there will be miss. So you can see there are two cases. Either there will be cache hit or there will be cache miss. Now when there is a cache hit, then what is the total access time seen by the CPU? That is same as hit time, cache hit time, or I can say cache memory access time. So I can say TC, cache memory access time. And when there is a, this will be cache miss. So you can see, and when there is a cache miss, then can you tell me what is the total time seen by the processor when there is a cache miss? What is that? According to Karl Hemmecher, that is miss penalty. Yes or no? Because according to Karl Hemmecher definition of miss penalty is basically the total time seen by the CPU when the requested data is not in the cache memory. Okay, it includes the time to check the cache memory also. In the definition of miss penalty by Karl Hemmecher, the time to check the cache memory for hit or miss, that is included. So remember, when the CPU will generate the memory request, first we will go to the cache memory. Either there will be cache hit or cache miss. When there is a cache hit, then what is the total access time seen by the processor? That is cache memory access time, or I can say cache memory hit time. This is cache memory hit time. And when there is a cache memory miss, when the requested data is not in the cache memory, then what is the total time? Total time seen by the processor, that is basically miss penalty according to Karl Hemmecher. Now you can easily write the formula. So average memory access time formula according to Karl Hemmecher book, that will be hit rate into TC. Okay, when there is a cache hit, then the total access time seen by the processor, that is cache memory access time, plus miss rate. When there is a cache miss, then the total access time seen by the processor, that is miss penalty. So let me write it capital M. So that's it. So you can see this formula, either you can understand logically or you can derive this formula from our previous formula that was using the miss time. Okay, I hope you understood the overall point. So you can see this is the screenshot from Karl Hemmecher book, let me tell you. And you can see here average memory access time formula, you can see here. But please understand, here this M, this miss penalty, this includes the time to check the cache memory for hit or a miss, because you can see here that we refer to the total access time seen by the processor when there is a miss as miss penalty. And please understand, this formula we will use only if the question explicitly says that miss penalty includes the time to check the cache memory. So remember here this note, use this formula only if the question explicitly says that miss penalty includes the time to check the cache memory. If this is given in the question explicitly, then you have to use this formula, because now the miss penalty, that is basically same as miss time. Okay, very simple. Now we are going to solve some standard university questions and some gate questions. And in all these gate questions, you will see there is no ambiguity. There is no ambiguity, and you don't have to worry about the definition of miss penalty, because everything will be given in the question. So let's solve this question from the Berkeley University. You can see source is UC Berkeley CS 162. So let's solve this question. Read this question and find the answer. The question is saying that consider a memory system with a cache memory. Cache memory access time is 10 nanosecond and main memory access time, that is 110 nanosecond. Now there is a statement given in this question that main memory access time, that is 110 nanosecond, and we are writing that assume that the memory access time includes the time to check the cache memory. Read this line. Remember, when we have single level cache memory, then main memory access time, that is same as miss penalty. Yes or no? But here you can notice that the question is saying that the main memory access time is 110 nanosecond, and this line is given to us that we need to assume that the main memory access time, this includes the time to check the cache memory. Okay, so remember, when you apply this main memory access time, then you don't have to extra include the time to check the cache memory. You don't have to extra include, because that is already included in this main memory access time. I hope you understood this point. Now, if the effective cache now if the effective access time means average memory access time, if that is 10% greater than the cache memory access time, then what is the hit ratio? So this is a very simple question. Now you can very easily solve it. So this is a beautiful question because this assumption is given in this question. So there is no ambiguity here. You can immediately solve this question from the information that is given here. So you can see we have cache memory access time 10 nanosecond, main memory access time 110 nanosecond, and the main memory access time, this assumption is given that it includes the time to check the cache memory. So very simple, the average memory access time that will be equal to, when there is a cache hit means hit rate multiplied by, when there is a cache hit, then what is the total access time seen by the CPU? Can you tell me? When there is a cache hit, when there is a cache hit, then the total access time seen by the CPU, that is basically cache memory access time, means 10 nanosecond. Because when there is a cache hit, then we don't have to access the main memory. So the total access time seen by the CPU, that will be 10 nanosecond. So I can say this 10 plus, when there is a cache miss, this is the miss rate. When there is a cache miss, then what is the total access time seen by the CPU? Can you tell me? That is 110. Remember, that is not 110 plus 10, because you can see when there is a cache miss, see, when the data is not available, when the requested data is not available in the cache memory, then what is the first thing? First thing is we check the cache memory. The CPU will generate the memory request. The first thing is we will check the cache memory if there is a hit or a miss. Then when there is a miss, then we will go to the main memory. But here you can see that main memory access time, this includes, this assumption is given to us that the main memory access time includes the time to check the cache memory. So you can see if the requested data is not in the cache memory, then what is the total access time seen by the CPU? What is the miss time? Miss time means what is the total access time seen by the CPU when the data, when the requested data is not in the cache memory? That is basically 110 here. Yes or no? So very simple. Miss rate multiplied by 110. So finally you can see it will be 10h plus 110 minus 110h. And you can see the question is saying that the average memory access time, that is 10% greater than the cache memory access time. You can see the cache memory access time is 10 nanosecond. So what is average memory access time here? That is basically 10% greater than cache memory access time. So cache memory access time plus 10% of this, you can see 10% greater than cache memory access time. So what is the 10% of this? You can see 10 into 10 divided by 100, this will be the 10% of 10. So basically that is 1. So you can see it will be 11 nanosecond. So you can see the question is saying that average memory access time, that is 11 nanosecond. And from here you can calculate the value of h. So that will be 100h is equal to 99. So h is equal to 99%. So the hit rate is basically 99%. So for this question, you can see what is the hit ratio. The question is asking the hit ratio. So that will be 0.99. This will be the answer. Very simple. You can see this is the answer. Hit ratio is 99 by 100. So I hope you understood this question. So in this question, this assumption is given to us. So there is no confusion. There is no ambiguity in this question. Let's solve this gatecse 2016 question. A file system uses in-memory cache for cache disk blocks. The miss rate of cache is shown in the figure. This is the miss rate given to us. The latency means access time. The latency, the access time to read a block from the cache memory, that is 1 millisecond. Milli means 10 power minus 3. So that is 1 millisecond. And to read a block from disk, that is 10 millisecond. Assume that the cost of checking whether a block exists in the cache is negligible. Read this line, what this means. This is an important line. The question is saying that assume that the cost of checking whether a block exists in the cache or not, that is negligible. Means checking the cache memory for a hit or a miss, that time is negligible. Is this clear? Very simple. This statement is given to us that assume that the cost of checking whether a block exists in the cache is negligible. When you are checking the cache memory for a hit or a miss, then that time, that lookup time is negligible. We can ignore it. Available cache sizes are in multiple of 10 MB. You can see the cache sizes, these are available: 10 MB, 20 MB, 30 MB, 40 MB. These are the available cache sizes. And this miss rate is given to you. For example, you can see when the miss rate is 40, for example, you can see when the cache size is 30 MB, then the miss rate is 40. When cache size is 70 MB, then the miss rate is 20. When the size of cache memory is 10 MB, then the miss rate is 80. So this diagram is given to us. The smallest cache size, the smallest cache memory size required to ensure that average read latency, average memory access time to read, that is less than 6 millisecond. So what will be the answer? So let's write the average memory access time formula for this question. AMAT, average memory access time. So that will be equal to, remember, there is only read operation in this question. There is no information about the write operation. The question is asking only for the read latency, the average memory access time for read operation, and the details are also given for the read operation. So you don't have to worry about read, write, okay, because here in this question, the operation is only the read operation. Okay, now let's solve this question. So you can see average memory access time, that will be equal to, remember, notice one thing. In this question, we are using the cache memory not for main memory blocks. We are using the cache memory for disk blocks. Okay, so basically in this question, you can assume that, so in this question, you can assume instead of CPU, there is a file system. So this file system, you can assume like this is CPU. Okay, then we have cache memory. But remember, we are using the cache memory not for main memory blocks. We are using the cache memory for disk blocks. Okay, very simple. So you can see we have cache memory, we have disk, that's it. Okay, now when this file system or this CPU, when this will generate some request, when then for that request, first we will go to the cache memory. We will check in the cache memory if there is a hit or a miss. If there is a hit, then we don't have to access the disk, because we just need to access the cache memory. But when there is a miss, but if the sorry, but remember, if the requested data is not in the cache memory, then first we will check the cache memory for hit or a miss. Now we found that there is a miss. Now when there is a miss, then we will access the disk. Okay, so very simple. So here, what will be the average memory access time? AMAT, average memory access time, that is equal to, when there is a hit, then we will only access the cache memory. We will not access the disk. Yes or no? So I can say hit rate multiplied by cache memory access time. Very simple. Because remember, when there is a hit, or I can say when the requested data is present in the cache memory, then we will only access the cache memory. So you can see hit rate multiplied by cache memory access time, plus when the requested data is not in the cache memory, then what we will do? Then first we will check the cache memory. If there is a hit or a miss, we will find that there is a miss, then we will access the disk. But remember, there is a one line given in this question that assume that the cost of checking whether a block exists in the cache is negligible. So please understand, if the requested data is not in the cache memory, then first we will check the cache memory whether there is a hit or a miss, but that time is negligible. That time is negligible. The question is saying that that time is negligible. So what we will do? So I can say when there is a miss, I can say miss rate multiplied by when there is a miss, then checking the cache memory, that is negligible. So I will directly access the, so we will just include the disk access time. Yes or no? Disk access time. I hope you understood this point. Please understand, please understand, we are just using the data that is given in this question, the information that is given in this question. Again, I'm telling you, the question is saying that the cost of checking, the cost of checking the cache memory, that is negligible. So if the requested data is not in the cache memory, then remember, first we will check the cache memory. Now we found that there is a cache miss, then we will access the disk. But remember, if the requested data is not in the cache memory, then the time to check the cache memory, that is negligible. Okay, so that we don't have to include. So when the data is not in the cache memory, then we will just include the disk access time. So you can see heat rate multiplied by cache memory access time plus miss rate into disk access time. And remember here, we are not doing TD plus TC. The reason is very simple, because the question has told us that checking the cache memory, that is negligible. Okay. Yes, in this question, you can assume that disk is basically the main memory and this file system is basically the CPU. Okay, like this. If you want to assume, then you can assume that disk is basically your main memory and this file system is basically CPU. That kind of mapping you can assume if you want. Okay, but anyway, this is the formula for average memory access time. I hope you understood how this formula is coming here. This line is very important, that the cost of checking the cache memory is actually negligible. Okay, is this clear? Now let's solve this question. So so you can see in this question, the hit rate of cache memory is not given to us. So let's assume that is h. We need to find the value of h. And from the value of h, we need to find the cache memory size also using this diagram. Okay. So you can see, let's assume the hit rate is h. And what is the cache memory access time? You can see cache memory access time, that is 1 millisecond. Means when you read a block from cache memory, then it will take only 1 millisecond. So cache memory access time, that is 1 millisecond, and the disk access time, that is 10 millisecond. So here average memory access time, that is, the question is saying that average memory access time should be less than 6 millisecond. So remember, this entire value, this should be less than equal to 6 millisecond. You can see here that the average latency should be less than 6 millisecond. So remember, this average memory access time, this should be less than 6 millisecond. This is what the question is saying. Average latency for read, that is less than 6 millisecond. Okay. So this is the equation we got. Now in this equation, we can put the value of h. We need to find out the value of TC, cache memory access time, that is 1 millisecond, plus 1 minus h, disk access time, that is 10 millisecond. This is less than 6 millisecond. Remember, the entire data is given in the millisecond, so you don't have to worry about the unit, because the disk access time, that is also 10 millisecond, cache memory access time, that is also 1 millisecond. So you can see everything is given in the millisecond. Okay, so from here you can see it will become h plus 10 minus 10h less than 6. So the hit rate should be greater than 40.44%. But remember, in the table that is given in this question, here they are discussing the miss rate. So let's find the miss rate also. You can see the hit rate is greater than 44.44%. And we know what is miss rate. Miss rate is basically 1 minus hit rate. So I can say, if hit rate is greater than this value, what will be the miss rate? Miss rate should be less than, because hit rate we have found in the percentage. So I can say miss rate, basically I can remove this from 100. Okay, so I can say miss rate will be less than 55.56%, because hit rate is greater than this value, so miss rate will be less than this value. Okay, so we have found that miss rate should be less than 55.56. Okay, this is what we have found, that miss rate, this should be less than 55.56 percentage. Okay, in the percentage we have found. So tell me, what is, so miss rate should be less than 55.56 percentage. And remember, the question is asking for the cache size, and the question is saying that available cache sizes are multiple of 10 MB. Means only these are the available cache sizes: 10 MB, 20 MB, 40 MB, 30 MB, like that. Okay, so here you can see we want to find what is the smallest cache size. So first of all, miss rate should be less than 55.56%. So tell me, in this chart, which miss rate is less than 55.56%? You can see 55 will come somewhere here. This is 55. Okay, you can see miss rate is, you can see miss rate is on the y-axis. So you can see this 55 will come somewhere here. So which miss rate is less than 55.56? That is directly 40. Yes or no? You can easily see. Okay, that is directly this point. So you can see that miss rate should be less than 55.56 percentage. And because the cache memory sizes available are only these 10 MB, 20 MB, 30 MB, 40 MB, and so on. So you can easily see that if I want smallest cache size, then that will be equal to 30 MB. Okay, you can see because miss rate should be less than this value, and I want smallest cache size. Because I want smallest cache size, so I will not consider these 40 MB, 50 MB, these I will not consider. I want smallest cache size. So you can see this smallest cache size is 30, for which the miss rate is also less than 55%. So for this question, the answer will be 30. 30 MB is the smallest cache size for this question. Very simple. I hope you understood. Let's all GATE 2004 question. Consider a system with two level cache. The access time of level 1 and level 2 cache memory and main memory, that is 1 nanosecond, 10 nanosecond, 500 nanosecond respectively. The hit rate of L1, L2 cache memory is 0.8, 0.9. What is the average access time of the system ignoring the search time within the cache? Read this line. We need to ignore the search time within the cache. Let's assume the requested data is not in L1, also not in L2. Then also, what we need to do when the CPU will generate the memory request, first we will go to the L1 cache, we will search in the L1 cache whether there is a hit or a miss. But this search time we need to ignore. Now, once we find that there is a miss, then we will go to the L2 cache. In this L2 cache, we will check whether there is a hit or a miss. This search time we need to ignore. And now, when there is a miss in the L2 cache, then we will go to the main memory. We need to access the main memory. So this is what this statement means, that we need to ignore the search time within the cache memory. We need to ignore the search time within the L1 cache. We need to ignore the search time within the L2 cache. Okay, so when the data is not available, when the requested data is not available in L1, L2 both cases, then I can say we need to ignore the L1 search time, L2 search time, and we directly have to access the main memory. Okay, so let's write the average memory access time formula here. That is very simple. When there is a hit, this is so let's write the average memory access time formula here. When there is a L1 hit, I can say the hit rate of L1. HL1, that simply means this is the hit rate of L1. L1 cache. So when there is a hit, in the L1 cache, then we will only access the L1 cache. Yes or no? Very simple. So I can say when there is a hit in the L1 cache, then the total access time seen by the CPU, that is basically L1 access time. So I can say L1 access time plus when there is a miss in the L1 cache, means the miss rate of when there is a miss in the L1 cache, then this is the miss rate of the L1 cache. Now there are two possibility. The two possibility are either L2 cache will hit or L2 cache will miss. Yes or no? So when there is a miss in the L1 cache, and let's assume there is a hit in the L2 cache. So hit rate of L2 cache into miss rate of L1 cache. In this situation, you tell me what is the total access time seen by the CPU. In this situation, please understand the data is not available in the L1 cache, but the data is available in the L2 cache. In this situation also, when the CPU will generate the memory request, first we will go to the L1 cache, we will search in the L1 cache whether there is a hit or a miss, but this search time we need to ignore. After there is a miss, after we find that there is a miss, then we go to the L2 cache, and when there is a hit in the L2 cache, then we will access the L2 cache. So I can say that when there is a miss in the L1 cache and hit in the L2 cache, then what is the total access time seen by the CPU? That is basically L2 access time. Because we need to ignore the search time within the cache memory, so we will ignore the search time within the L1 cache memory. So here I can say that in this situation, when there is a miss in the L1 cache, hit in the L2 cache, in this situation, the total access time seen by the CPU, that is basically access time of L2 cache. But remember, there is another situation, that is when there is a miss in the L1 cache also. So this is the L1 miss rate. And when there is a miss in the L2 cache also, this is the miss rate of L2. In this situation, means the data is not available in L1, also the data is not available in L2. In this situation also, when the CPU will generate the memory request, first we will search in L1, that search time we need to ignore. Then we search in L2, that search time we need to ignore. And then we will access the main memory. So when there is a miss in L1, L2 both, then what is the total access time seen by the CPU? That is basically main memory access time. Yes or no? So here it will be main memory access time. That's it. So very simple. I hope you understood. So here you can see. So here you can just put the data and you can calculate the average memory access time. The hit rate of L1 cache that is given to us, that is 0.8. This is the hit rate of L1 cache. So I can say 0.8 multiplied by L1 access time. L1 access time is 1 nanosecond plus. Remember, all the access time they are given in nanosecond, so you don't have to worry about the unit. Okay, next you can see 1 minus HL1, that is basically 0.2, means this is the miss rate of L1. When there is a miss in L1 and hit in L2, what is the hit rate of L2? That is 0.9. The question is saying hit rate of L2, that is 0.9. So in this situation, we need to ignore the search time within the L1 cache. So in this situation, basically the total access time seen by the processor, that will be access time of L2 cache. Access time of L2 cache is 10 nanosecond, so multiplied by 10 plus when there is a miss in L1 comma L2 both, so the miss rate of L1 that is 0.2, miss rate of L2 that is 0.1. In this situation, we need to ignore the search time within L1 comma L2 cache. So the total access time seen by the processor, that will be basically main memory access time, and main memory access time, that is 500 nanoseconds. So I can say multiplied by 500. You can calculate this equation, this value, and that will be your average memory access time. So the average memory access time, that will be equal to 0.8 plus 1.8 plus 10. So that will be equal to 12.6 nanosecond. This will be the answer. So quite simple question, but remember in this question, focus on this statement. They are saying that we need to ignore the search time within the cache memory. So if the data is not available in L1 cache, also not in L2 cache, then remember when the CPU will generate the memory request, first we will search in the L1 cache, we will search in the L2 cache. That time we need to ignore. So directly we need to just include the main memory access time. Okay, the total access time seen by the processor when there is L1 miss, L2 miss, then the total access time seen by the processor is basically main memory access time. Okay, so I hope you understood the meaning of this last statement. And for this question, the answer will be 12.6 nanosecond. Okay, see 13 nanosecond will come, but if you don't if you don't focus on this statement, then 30 nanosecond also will come, and that is given in the option. If you don't focus on this statement, if you don't, then this 30 nanosecond is also there in the option. Okay, so please apply what is given in this question. Okay, is this clear? For this question, answer will not be 13, the answer will be 12.6, and both the options are given, remember. So please take care. Okay, so that's it. So we have seen the complete chapter, average memory access time for single level cache, for multi level cache. We have seen everything related to average memory access time. I hope you understood everything. We have done a lot of questions, a lot of gate exam questions, standard university questions, MIT question, Berkeley question, and I have tried that you have crystal clarity about everything. Every question that you solve, you should solve with crystal clear understanding, without any confusion, without any doubt, without any ambiguity. You can see all the questions that we have done, each and every question with very clarity we have solved it. Okay, so I hope you are feeling confident in this average memory access time. Now, let me discuss one optional topic, that is look aside cases. I told you in the previous lecture that I will discuss at the end, I will discuss what are look aside cases. Okay, because there is a misconception related to look aside cases. Actually, in some gate exam questions, some people, some teachers, some students, they use the concept of look aside cases, and that is wrong. Let me tell you. That is what I want to discuss. So, let me discuss what are look aside cases, what is the look aside model, what is the look through model. Let me define them, and also let me share with you, if look aside cases are given in the question, then what will be the average memory access time. But remember, there is no gate exam question based on look aside cases. That is the reason I've made it optional. This is an optional topic. Let's study this topic, and after that you can forget about this topic, because this is not required for the gate exam. There is no gate exam question based on look aside cases. Okay, So let me tell you, so far everything that we have seen, that is basically look through cache design. So far what we have seen that cache memory is placed between CPU and main memory. Okay, yes or no? This is CPU and this is the main memory. So what we do, we put the cache memory between CPU and main memory because we have a memory hierarchy in our systems. In the modern processors, we have memory hierarchy. We put the cache memory on the processor chip between CPU and main memory. So whenever the CPU will generate memory request, remember CPU does not know about the cache memory. CPU does not know about the levels of cache memory. CPU only knows about the main memory. So CPU will generate the memory request, main memory request. But with that main memory request, because cache memory is placed between CPU and main memory, so when the CPU will generate the memory request, you can see, then we will go to the cache memory. We will check in the cache memory whether there is a hit or a miss. If there is a hit, then we will transfer the data to the CPU. But when there is a miss, then this cache memory, this cache controller, this will transfer the memory request to the main memory. Now what we will do, from the main memory, from the main memory block of data, we will transfer to the cache memory, and then from the cache memory, we will transfer the word to the CPU. So this is what we have seen. Let me tell you, this entire design, this is called look through cache. So everything that we have studied so far, the memory hierarchy, everything that we have seen, that is basically called look-through design. The name itself is telling you look through, means the cache memory is placed between CPU and main memory, and whenever the CPU want to access the memory, whenever the CPU will generate the memory request, we always have to look through the cache. Okay, we always have to go through the cache, I can say. So you can say this is basically go through. Okay, but the name is the official name, the standard name, that is look through cache. Okay, so this look through cache design we have studied so far, everything that we have seen so far, that is basically look through cache design. Okay, very simple. So let me tell you about the look through cache design. So look through cache design recap. You might be thinking we have not seen look through cache. Actually, we have seen everything that we have seen so far, that is basically look through cache design. Okay, so that is the reason I am calling it recap. So you can see what happens in a look through cache. We put the cache memory between CPU and the main memory. So the processor will access the cache first. You can see when the processor will generate the memory request, first we will access the cache first. We will check whether there is a hit or a miss. If there is a hit, then we will transfer the data from the cache to CPU. If there is a miss, then the cache controller, the cache memory will forward the request to the main memory. Then we will fetch a block from main memory to the cache memory. We will put that block in the cache memory, and then from the cache memory, we will supply the word to the CPU. This is what we have seen so far in the memory hierarchy. This is what we do. And this is called look through cache design. Also, let me tell you, that in the modern CPUs, all the modern CPUs, Intel, AMD, ARM, all the modern CPUs, they use the look through caches. We will study look aside cache design. There is something called look aside cache design, but that is, I can say, non existent. In the modern processors, that is not used. Also, that was used in the older days only for some specialized systems, or I can say embedded systems. So in the main processors, that is not used. Okay, is this clear? Notice one thing, in the look through case, the main memory traffic, that is actually very less. What is the reason? Because CPU will access the cache memory. If the hit rate of cache memory is 90%, then 90% times CPU will access the cache memory. So 90% times CPU will not access the main memory. So you can see the main memory traffic, that is very, very less, I can say. So in this look through case, because we always access the cache memory first, and if there is a cache hit, then we never access the main memory. So you can see the main memory traffic, that is actually reduced. Okay, that is very less, or I can say that is reduced. So it will save so it will save power, and it will reduce the unnecessary main memory traffic. I hope you understood. And in all the modern CPUs, for L1, L2, L3 caches, we use the look through design. Also remember, all the standard books and all the gate PYQs, they follow the look through design. So notice one thing, what we have seen so far, everything that we have seen so far, if you notice that, that is actually defined as look through case, or I can say that is basically the definition of look through case. All the standard books, all the gate PYQs, they follow look through case design, or I can say they follow what we have seen so far. Let me ask you one disadvantage of look through case. Can you tell me? See, just think logically. If the data is available in the cache memory, then we need to access the cache memory. Very good. If the data is not available in the cache memory, then we need to access the main memory. But when the data is not available in the cache memory, then also we need to access the cache memory first, then we need to access the main memory. So in the look through design, or I can say everything that we have seen so far in the memory hierarchy, basically what we do, if the data is not available in the cache memory, then also we have cache memory access time plus main memory access time. What is the reason? Because first we have to search in the cache memory whether there is a hit or a miss. So if the data is not available in the cache memory, then also we have to search in the cache memory. So that is called lookup time. Yes or no? So I can say if the data is not available in the cache memory, we need to access the main memory, but still we have to search in the cache memory. So this lookup penalty, I can call it lookup penalty. Yes or no? So this lookup time we have to spend. Okay. I hope you understood this. I hope you understood that for every memory request, whether the data is available in the cache or not available in the cache, whatever happens, we always have to go through the cache. We always have to look through the cache. We have to look in the cache memory. We have to find whether there is a hit or a miss. If there is a hit, we will only access the cache memory. But if there is a miss, then also we have already spent some time for cache lookup. Okay, then we will access the main memory. So you can see if the data is not available in the cache memory, then also first we will spend the time to look in the cache memory, time to search in the cache memory, then we will access the main memory. Okay, so you can see, this screenshot I have taken from a standard book, and in this standard book you can see they are saying that there is a lookup penalty. Okay, what is the meaning of this lookup penalty? This simply means that if the data is not available in the cache memory, then also first we will check the cache memory. First we will search in the cache memory. First we will look up in the cache memory. Then we will access the main memory. So you can see when you use this look through cache, this is also called inline cache. The another name for look through cache, that is inline cache. So when we use look through cache, then I can say for every memory access, whether the data is available in the cache or not, for every memory access we have to look in the cache memory. Okay, so that is one thing. But remember, the memory traffic will be reduced, as I told you, because if the hit rate is 90%, then 90% times CPU will not even access the main memory. So main memory is free. So there is no main memory bus traffic, I can say, or I can say there is reduced main memory bus traffic. Okay, I hope you understood. So let's see the average memory access time formula for look through cache. This we have already seen because everything that we have studied so far, that is basically look through design. So tell me what will be the average memory access time formula in the look through design? In the look through design, if the data is available in the cache memory, means if there is a hit, then what is the total access time seen by the CPU? That will be cache memory access time plus when there is a miss, means when the data is not available in the cache memory, then what is the total access time seen by the CPU? Remember, if the data is not available in the cache memory, then also first we will look up in the cache memory. Yes or no? So I can say that cache memory access time plus main memory access time. Okay. So notice this TC. This is basically cache lookup time. Because when the data is not available in the cache memory, then also first we will search in the cache memory. So this is basically cache memory search time. I can say this is cache memory. This is cache memory search time, or you can say this is basically lookup time, or you can say this is lookup penalty. So when the data is not available in the cache memory, then also first we have to search in the cache memory. So you can see this is cache memory search time, or I can say this is the lookup time, or I can say this is the lookup penalty. This is not miss penalty. This is lookup penalty. Means if the data is not available in the cache memory, then also first we have to search in the cache memory. So that time we have to spend. That time we have to include. Then we will then we will access the main memory. So you can see the average memory access time formula for look through cache design, that will be this. And if you simplify this, what we are going to get after simplification, we will get that for every memory request, whether the data is available in the cache or not available in the cache memory, for every memory request, we will always spend this much time. We will always access the cache memory, right? And you can see when there is a miss in the cache memory, then what are the extra time we are spending? The extra time we are spending, that is main memory access time. So you can see if you simplify this entire formula, then you will get this simplified formula. So I can say for the look through cache design, this is the average memory access time formula. This is also average memory access time formula. And remember, everything that we have seen so far, that was basically look through cache design. This is also called inline cache. This is called inline cache because we put the cache memory between CPU and main memory. So I hope this point is clear. So you can see this look through cache. The main memory is accessed after the cache miss is detected. Yes or no? So I can say if we need to access the main memory, then also first we have to search in the cache memory. Yes or no? So you can see the main memory is accessed after the cache miss is detected. So this is look through design, and this is the formula. If you simplify this formula, you will get this formula. So this is what we have seen. Now let's discuss what is look aside cache design. The name itself is telling you look aside. Actually, in this look aside cache design, we don't put the cache memory between CPU and main memory. We put the cache memory in parallel with main memory. So this is the difference between look through and look aside. In the look through, we put the cache memory between CPU and main memory. So we always have to go through the cache memory. But in the look aside cache design, we we don't put the cache memory between CPU and main memory. We put the cache memory in parallel with main memory. So what will happen? You can see in this diagram. In this diagram, you can notice that we are putting the cache memory in parallel with main memory. Now what will happen? For every memory request, when the CPU will generate the memory request, that memory request will go to that memory request will go to cache memory also, that will go to main memory also. So please understand, every memory request made by the CPU will go to both cache memory and main memory. So you can imagine there will be a lot of main memory traffic. Yes or no? Like for every memory request, we are going to cache memory also, we are going to main memory also. Now let me tell you what will happen. Cache memory access time is very low and main memory access time is very high. For example, let's assume cache memory access time is 10 nanosecond and main memory access time, let's assume that is 500 nanosecond. So now you can see for every memory request, because cache memory and main memory, they are sitting in parallel. Cache memory is not between CPU and main memory. Cache memory is not between CPU and main memory. Cache memory is in parallel with main memory. So for every memory request, we will go to both cache memory and main memory. Now, because the cache memory access time is very less, like for example 10 nanoseconds, so what will happen? The request is going to both of them. If there is a cache hit, then we will ignore the result that we are getting from the main memory. You can see from CPU the memory request, every memory request is going to cache and main memory, but cache memory access time is very low. Like 10 nanosecond is the access time of cache memory, 500 nanosecond is the access time of main memory. So if there is a cache hit, then we will cancel this memory request. Okay, or I can say we will ignore this memory request. And you can see we will get the data, the CPU will get the data from the cache memory. But notice, if there is a cache miss after 10 nanos after 10 nanosecond, you will find that there is a cache miss. If there is a cache miss, then we will wait for the main memory. But notice one thing here. Here you can notice that if there is a cache miss, if the data is not available in the cache memory, then directly we are accessing the main memory, because for every memory request, the signal is going to the cache memory also and to the main memory also. Yes or no? So is this point clear? So very simple, let me explain. Sorry. So very simple, let me conclude that in the look aside cache design, the cache memory is not between CPU and main memory. This cache memory is placed in parallel with main memory. For every memory request, the request will go to cache memory and main memory both. Okay. Now, if there is a cache hit, then we will cancel this main memory request, and this CPU will get the data from the cache memory. But you can see, if the data is not in the cache memory, then we will get the data from the main memory. This is look aside cache design. Now you just tell me one simple point. In this look aside cache design, if the data is available in the cache memory, then what is the total access time seen by the CPU? If the data is available in the cache memory, then the total access time seen by the CPU, that is basically cache memory access time. Yes or no? But remember, if the data is not available in the cache memory, then what is the total access time seen by the CPU? If data is not available in the cache memory, then total access time seen by the CPU is basically main memory access time. Because remember, when the request was generated, that request was immediately sent to both cache memory and main memory simultaneously. Yes or no? So here I can say, when the data is not in the cache, then so here I can say when the data is not in the cache, then the total access time seen by the CPU, that is main memory access time. And when the data is available in the cache memory, then the total access time seen by the CPU, that is basically cache memory access time. Okay, is this clear? So let's see this. So let's see this look aside cache design. Cache memory is placed in parallel with main memory. On a memory request, when the CPU will generate the memory request, for every memory request, both cache memory and main memory will be accessed simultaneously. Means the memory request, every memory request will go to cache also, to the main memory also. Okay. If there is a cache hit, then we will cancel the memory request that is going to the main memory. So I can say main memory result is ignored, or I can say we will cancel the signal that we have sent to the main memory. And if there is a miss, if there is a cache miss, then the main memory result is already available. Okay, very simple. Now you can imagine what are the downside of this look aside cache design. Can you imagine what are the downside? See, the downside is very simple. For every memory request, we are accessing cache as well as main memory. Yes or no? For every memory request, we are accessing main memory. See, in the look through cache design, only when there is cache miss, then we are accessing the main memory. So if the hit rate of cache memory, let's assume that is 90%, then you can see in the look through cache design, only 10% times we were accessing main memory. But in the look aside cache design, if we have 90% hit rate of cache memory, then also for every memory request we are accessing the main memory. So there is a lot of memory traffic, I can say. Yes or no? So you can see this look aside design, this design will waste a lot of power, and the memory traffic is too much, or I can say, you can see the memory bandwidth that is also wasted. The memory traffic is too much because every request is going to the main memory, also to the cache memory. Yes or no? Also, let me tell you, this look aside cache design, this was sometimes used in the older processors. Also, let me tell you, this look aside cache design, this was sometimes used in the older days. Okay, not in the modern days. I can say in the modern processors, this look aside cache design is not used. Okay, because we have a memory hierarchy. We put the cache memory between CPU and main memory. We don't put the cache memory in parallel with main memory. Yes or no? So in the modern processors, we don't use this look aside cache design. This was sometimes used in the older days in the embedded em, in the embedded processors, or I can say some specialized processors. Let me also tell you one important point why this look aside cache design is not used in the modern processors. Because the modern processors, these are multi-processing, multi-programming. In the operating system, you will study the concept multi-programming, multi-processing. Okay, so you can see the modern processors, these are multi-processing. Okay, now you can notice in the look aside cache design, if we are executing some program, let's assume, then you can notice for every memory request we are accessing the main memory. Every memory request is going to the cache, also to the main memory. So this main memory is always occupied. So that is the reason when you are using the look aside cache design, then it will not support multiprocessing. It will not support multiprocessing. That is the reason this look aside cache design is not used in the modern processors. This was used in the older days in some embedded systems. Okay, but this is no longer used, and I can say this is, I can say, non-existent concept nowadays, or I can say this is basically, this is basically now just a theoretical, or I can say just a historical concept. Okay, this is not used in any modern processor. Also, there is no gate exam question based on look aside cache design. I hope you understood the disadvantage of look aside cache design. You understood the difference between look aside cache design and look through cache design. Okay, you can see this screenshot I've taken from a standard book. This is for look aside cache design, and you can easily see that this was this was fine in the older days. This was fine for single processor, for single tasking systems. The reason is very simple, because main memory is involved in every operation. For every memory access, we are sending the signal, we are sending the request to both main memory and cache memory. So this was fine for single processing system, or I can say single tasking system. But read this line, this important line, you can notice, but it will work to detriment, means it will, detriment is a negative word, right? It will worse, it will ruin. Okay, but it can work to detriment of multitasking systems and multiprocessing systems. Okay, because the reason is very simple, since the cache memory will allow the CPU to waste considerable amounts of main memory bus width. Is this point clear? Because you can see, even if cache memory has 90% hit rate, then also for every memory request, CPU is sending the memory request to both main memory and cache memory. That is the reason you can see that we are wasting considerable amount of main memory bus width. Okay, so that is the reason this look aside cache design, this was fine in the older days, you can see, for single tasking system, for single processor system. But notice, for multitasking systems nowadays, our processors, our modern processors, these are multitasking systems, and for these, this look aside cache, this will be detriment, or I can say this will be worse. I hope this point is clear. But let's see what the average memory access time for look aside cache design. This is not required for the gate exam, because as I told you, in the gate exam there is no question based on look aside cache design. This is historical concept. In the older days this was used, no longer this is used. There is no gate exam question based on this look aside cache design. There is no standard book, there is no famous standard book which covers look aside cache design. All the standard books like Carl Hemacher, Patterson and Hennessy, William Stellings, Morris Mano, all the famous standard books that are followed by NPTEL, that are followed by IIT professors, they only cover look through cache. Okay, they don't cover look, they don't cover this look aside cache design, because this is for older days, because this is historical only, no longer used. But anyway, let's see the average memory access time formula. So for look aside cache design, what will be average memory access time formula? That is very simple. When there is a hit in the cache memory, then what is the total access time seen by the processor? Can you tell me? Remember, every memory request generated by the CPU, that is going to cache memory also, to the main memory also. Okay, when there is a hit in the cache memory, then the CPU will get the data from the cache memory, and CPU can just cancel this memory request to the main memory. So I am asking, when there is a hit in the cache memory, then what is the total time, total access time seen by the processor? That is basically cache memory access time. And when the data is not available in the cache memory, now you tell me, what is the total access time seen by the processor? If the data is not available in the cache memory, then the total access time seen by the processor, that is basically main memory access time, because the signal, the memory request went to cache memory and main memory simultaneously. So you can see, if the data is not available in the cache memory, then also we can access the data from the main memory. So I can say the total access time seen by the processor, that is basically main memory access time. So that's it. This is the average memory access time formula for look aside cache design. Okay. Remember one thing. So far in the GATE exam, there is no question based on this look aside cache design. But in the future, if they ask you a question, and in that question they explicitly mention, in the question it is mentioned that we are using the look aside case, or they mention that cache memory is placed in parallel with main memory. Cache memory and main memory, they are parallelly placed, and every memory request is going to both cache and main memory. Basically, if look aside word is given in the question, or if the look aside definition is given in the question, only in these two cases you need to apply this formula of uh, all India, this formula of average memory access time. Is this clear? But so far in the gate exam, there is no question which mentions look aside case or which gives the definition of look aside case. So far, all the gate exam questions, these are based on look through cache design. Okay. And we have already seen look through cache design. We have done a lot of questions, standard questions, gate exam questions. Okay. So you can see this slide, look aside cache. Main memory is accessed concurrent with cache memory. Main memory is placed in parallel with cache memory. And if there is a cache hit, then we will abort the main memory access. And if there is a cache miss, then already the main memory access is going on, that is already in progress. So you can see wasted main memory bus cycles, because for every memory request we are going to cache also main memory also. So you can see wasted main memory bus cycles on cache hit also, on cache miss also. Okay, if there is a 90% hit rate, then also you can see for cache hit also we are wasting the main memory bus cycles. Okay, yes or no? And you can see this is a big problem if the memory is shared. Means if you have multitasking systems, multi-programming systems, then this is a big problem. That is the reason this look aside case, this was used in the older days for single tasking system, for single processing system, this was fine. But for modern processors, for multitasking, multi-programming systems, this look aside cache design, this is a big problem if the memory is shared. Means memory shared means this is a multi-programming, multitasking system. So you can see this look aside cases, these are no longer used, because nowadays all the modern processors, these are multi-programming, multitasking. Okay, so you can see for look aside cases, this is the average memory access time. Now, let me tell you some important notes. These important notes we have already seen in the previous lecture also. Let me repeat them so that there is no confusion. So let me tell you, you may have seen this word simultaneous access, parallel access. This you may have seen. Let me tell you, this is not a standard terminology. There is no standard book, there is no standard resource, there is no university notes, NPTEL books, there is no standard resource which mentions such terminology. This simultaneous access, parallel access, this terminology is not mentioned in any standard resource. Okay, there is no gate exam question based on this imaginary self-made terminology, that is simultaneous access. There is no gate exam question based on this terminology. This is a imaginary, or I can say self-made terminology by some people. Okay, this is not a, not something given in the standard resources. Also, we will not use this terminology, this simultaneous access. Did you notice so far I never used this simultaneous access, this terminology? Yes or no? Because we always follow the standard books and the standard resources as always. Let me tell you important note too. If you follow the widely followed standard books, if you study Hennessy and Patterson, Morris Mano, William Stellings, Carl Hemacher, all these are very famous computer architecture books. These are followed in IITs, ISC Bangalore, in the NPTEL. These are the most followed computer architecture, computer organization books. Let me tell you, no widely followed standard book covers or mentions look aside cache design. The reason is very simple, because it is not used in the modern processors. Why it is not used in the modern processors? Because it will access the main memory on every access. Okay, for every memory request generated by the CPU, we will access the main memory. That is the reason I can say it is not suitable for the multitasking or multiprocessing systems. That is the reason I can say that this look aside cache design, let me tell you, this you will never find in any widely followed standard books when you study All these books like William Stellings, Maurice Mano, Carl Hemmetzer, Hennessy Peterson, if you study all these books, you will never find this concept look aside cache design. You will never find, because it is not used in the modern processors. Also, you can see that no gate exam question is based on look aside cache design. Okay, this look aside cache design, this is more of a historical or theoretical model. This is rarely used, or I can say not used, in the modern processors. This was only seen in some older or embedded systems. We have already seen. One more very important note I want to discuss with you, that is, I have seen some students, actually many students I have seen, they confuse or relate this following formula with so called simultaneous access or look aside cases. Whenever they see this formula, HC means hit rate multiplied by cache memory access time plus miss rate into main memory access time. Whenever they see this formula, then immediately they think that this is simultaneous access. Actually, this simultaneous access, this is not even a standard terminology, but I can say they think that this is a look aside case. But let me tell you, this is wrong. This is actually a misconception. This formula does not imply that we have look aside cases. If you remember, this formula we have seen in the look through cases also. And if you remember, this formula we use when the miss penalty includes the search time in the cache memory. Yes or no? Do you remember this formula is used by the Carl Hemmetzer book? And the Carl Hemmetzer says that miss penalty includes the search time in the cache memory. Okay, so remember, this formula is sometimes used in the look through design. This formula is sometimes used in the hierarchical access, or I can say in the average memory access time in the memory hierarchy. Sometimes we use this formula. And when do we use this formula? Can you tell me? We have already seen many questions. We have already seen the Carl Hemmetzer questions, the Carl Hemmetzer definition, and some questions from Berkeley University, from gate exam. We have already seen some questions. So you can see, when do we use this formula? This formula we use when the question says that miss penalty includes the search time in the cache memory, or when the question says that we ignore the search time in the cache memory, or when the question says that the search time in the cache memory is negligible. Basically, if this is given in the question that the lookup time in the cache memory, or I can say search time in the cache memory, that is negligible, or that is included in the miss penalty, or that can be ignored, when this type of things are given, then we use this formula. So please understand, this formula has nothing to do. So please understand that this formula does not imply look aside cases. Yes, for look aside cases also we have this formula, but this formula we also have for hierarchical access, or I can say for the average memory access time in the memory hierarchy for look through design. Okay, is this clear? So you can read this. Some students, they confuse or relate the following formula with look aside cases or so-called simultaneous access. When they see this formula, immediately they think that okay, this is simultaneous access, this is look aside cases, but this is wrong. This is misconception. Actually, they think that if this formula is applied in any question, then the cache design is basically look aside, or I can say so-called simultaneous access. But let me tell you, this is actually a misconception. This formula is also a hierarchical access formula. This formula is also used in the look through cases. When do we use this formula? We use this formula when the cache lookup time is ignored, or it is negligible, or it is included in the miss penalty definition. We have already seen Carl Hemmetzer definition of miss penalty. In the Carl Hemmetzer, the miss penalty definition includes the cache memory search time, the cache memory lookup time. Or when the question says that cache memory lookup time can be ignored or it is negligible, in these situations we use this formula. Okay, so please don't relate this formula with so-called simultaneous access. There is no gate exam question based on so-called simultaneous access. There is no gate exam question based on look aside case. Sometimes this formula is used when the sometimes this formula is used in the hierarchical access, or I can say in the look through cache design, when the main when the cache memory lookup time, cache memory search time is said to be ignored or negligible, or it is said to be included in the miss penalty. If you remember, we have already seen many questions. You can see this is the question from UC Berkeley, from Berkeley University. This question we have seen, and read this line. Assume the memory access time includes the time to check the cache memory. Yes or no? This statement is given. So because of this statement, when the data is not available in the cache memory, then the total access time seen by the CPU, that is basically main memory access time. Yes or no? So you can see, because of this statement in this question, remember, this question is not look aside design. This question is not so called simultaneous access. This question is simple memory hierarchy look through design. We have a memory hierarchy. There is a cache memory between CPU and main memory. Okay, this is a very simple main memory question. This is a very simple memory hierarchy question. So what will be the average memory access time formula? That will be when the data is available in the cache memory, means when there is a cache hit, then the total access time seen by the CPU, that will be cache memory access time, plus when the data is not available in the cache memory, means there is a cache miss. In this situation, the total access time seen by the CPU, that is basically 110. Okay, and you can see in this main memory access time, this cache memory search time is included. So you can see, you can notice that in this question, which is pure, I can say, which is very simple question based on look through design, or I can say based on memory hierarchy design. But you can see in this question also we are using this formula. Yes or no? Because the reason is very simple. The question says that cache memory search time, cache memory lookup time, that is included in the miss penalty. Yes or no? You can see this answer. Also we have seen this gate Also, we have seen this GATE 2016 question. In this question also, you can see this line is given. Assume that the cost of checking whether a block exists in the cache memory is negligible. Yes or no? So here also you can notice cache memory lookup time, cache memory search time is negligible. Very simple. This question also we have done. You can also see this GATE 2004 question. Here we are saying that we need to ignore the search time within the cache memory. So in this question also, the lookup time, the search time within the cache memory, we need to ignore. All these questions we have done. So I hope you understood. So please understand that this formula does not imply look aside cases, or this formula does not imply the so-called simultaneous access. Is this clear? This formula we use in the hierarchical access when the cache memory search time is said to be ignored, or it is said to be negligible, or it is said to be included in the miss penalty, or it is said to be included in the main memory access time. In these situations, we use this formula in the hierarchical access, or I can say in the look through cache design. Okay, is this clear? So this formula does not imply look aside cases. This formula does not imply so called simultaneous access. This meme you can see, I have seen many students actually, when they see this formula, hit rate into cache memory access time plus miss rate into main memory access time, when they see this formula, then many students, what they do, they immediately say that this is the simultaneous access, this is the look aside access, and these things are misconceptions. I have already discussed it. Okay, so that's it everyone. So we have seen everything in this lecture. In the previous lecture, also in this lecture, we have seen the complete concept of average memory access time, hit time, miss penalty, hit rate, miss rate. We have seen we have seen standard questions. We have done a lot of standard questions, gate exam questions. We have seen the misconceptions of simultaneous access, misconception related to look aside cases. There is no gate exam question based on look aside cases. There is no gate exam question based on so-called simultaneous access. All the gate exam questions, these are based on memory hierarchy design. Cache memory sits between CPU and main memory. Every memory request goes through the cache memory. When there is a cache miss, then we access the main memory. When there is a cache hit, we don't access the main memory. So all these concepts we have seen. We have seen the memory hierarchy, we have seen multi-level caches, we have seen average memory access time in case of single level case, in case of multi-level case. So all the concepts we have seen. I hope you are comfortable, I hope you are confident. And let me promise you one thing: after watching these two lectures, you can solve all the gate exam questions, all the standard questions with confidence, because there is no ambiguity. We have already done a lot of standard questions, a lot of gate exam questions, and all the questions we have done with a lot of confidence, without any ambiguity, without any confusion. That is the power of learning the correct concept. If you follow the standard resources, you will learn the correct concepts, and then you can solve the questions very easily. But if you study from non-standard sources who are teaching you self-made concepts, then you will get confused. In this question, should I apply simultaneous? Should I apply hierarchical? In this question, this given, so it is hierarchical. This given, so it is simultaneous. Okay, I have seen this. Okay, and uh, I just want to ask, from where these concepts are coming, from where this terminology is coming, simultaneous access. So anyway, so let's forget it. In the next lecture, we will study global miss rate, local miss rate when we have multi-level cases. I told you when we have multi-level cases, then there are two type of miss rate: global miss rate, local miss rate. Also, we will study inclusion property in multi-level cases. Also, we will study inclusion property in cases in general. So, inclusion property we will study when we have multi-level cases. Also, we will study when we have multiple cases in general. Okay. So, these concepts we will study in the next lecture. Okay. Thank you, everyone. Please like this session. If you understood everything, if your misconceptions got cleared, if you think that if you think that these lectures were useful, please like this session. Please share it with all the GATE aspirants. Please share with them that there are a lot of misconceptions and they can learn the correct concepts from these lectures. The part 1 you can find in the description. Also, please put your feedback in the comments. That is very important for these lectures. Average memory access time part 1, part 2. For these lectures, I will go through each and every comment. So, this is my request to you. If you found this lecture very helpful, you can share your honest feedback. Please put a comment. Okay. Thank you, everyone. Thank you so much.